Before we begin, take a moment to consider this. Wherever you are right now, whether curled up in bed, gazing at a darkened ceiling, sitting by a quiet window, or drifting off to the hum of the night, look inward and then outward and ask yourself the one question that has haunted scientists, philosophers, and poets for centuries. How big is everything really? Because when you look up at the stars, you're not just seeing points of light, you're staring into a past so ancient and a space so vast that your mind doesn't just struggle to grasp it, it begins to dissolve into it. The deeper you go, the more the edges blur. And it's in that blur, in that cosmic fog where numbers stop making sense and distances stretch beyond imagination, that the real story begins. In this video, we're not just going to talk about stars, galaxies, or redshifts. We're going to walk to the very edge of space and ask what lies beyond it, and if such an edge even exists. But before we begin, I want to ask you, where are you watching this from? Leave a comment below with your location and the time right now. And while you're here, help us reach 100 subscribers by hitting that button, because the universe may be infinite, but our journey is just beginning. Chapter 1. How big is the universe? Really? When we ask how big the universe really is, we often picture something physical, something we could theoretically hold in our minds, a vast spherical space full of galaxies, stretching outward like an enormous snow globe with no glass. But the truth is, no matter how far we stretch our imagination, the real answer slips just beyond our reach. Not because it's too far, but because the rules we use to measure ordinary things simply fall apart at this scale. We can talk about light years, about parsecs, about redshifts and cosmological constants, but even when we do, we are still only scratching the surface of something far more elusive, something that refuses to be measured in any way that feels intuitive to us as human beings. To begin understanding the scale of the universe, we have to start small, at least cosmically speaking. The observable universe, the part we can see from Earth because light has had time to reach us since the Big Bang, spans roughly 93 billion light-years in diameter. That number alone should be enough to take your breath away. Not because it's a number so large, but because it shouldn't be that large. The universe is only about 13.8 billion years old, and if nothing can move faster than light, then how on Earth, or more precisely, how in the cosmos, can we possibly see things nearly 100 billion light-years apart? The answer lies in the fact that the universe is not static. It's been expanding ever since the moment it came into being. And this expansion isn't like an explosion where matter flies out into space, because space itself is expanding. Galaxies aren't moving through space away from one another as if they were tossed into a void. Instead, space itself is stretching, carrying galaxies along with it, like raisins in a rising loaf of bread. The further away something is, the faster it appears to recede, not because it's accelerating through space, but because the space between us and that object is growing. This means that even though a galaxy's light might have taken 13 billion years to reach us, it began that journey in a much younger, smaller universe. But during that time, space has stretched so dramatically that the galaxy is now far more distant than it was when the light first left. What we see is not where it is, but where it was. The scale of the observable universe isn't determined just by the speed of light. It's shaped by the geometry of space-time itself, and how it's been stretching over time like a living, breathing fabric that never stops expanding. And still, we have to remember, this is just the observable universe. What lies beyond what we can see? That is where the question becomes not only scientific but almost spiritual. Because light from anything farther away simply hasn't had time to reach us yet. It's entirely possible, probable even, that the universe goes on far beyond that 93 billion light-year sphere, perhaps infinite. Or maybe it loops back on itself like a three-dimensional version of a two-dimensional video game screen, where if you exit one side, you enter from the other. The truth is, we just don't know. Cosmologists have run models, simulations, and surveys of galactic patterns, trying to guess whether the universe curves outward like a saddle, loops around like a hypersphere, or extends flat and endless in every direction. Right now, all evidence suggests that the universe is flat on a large scale, meaning that parallel lines stay parallel forever and space doesn't curve inward or outward significantly. But the problem is, even with that information, we can't say whether the flatness continues forever or whether it just appears flat from our vantage point, like the Earth seems flat when you're standing on it. So when we ask how big the universe is, we're not just asking about distance, we're asking something much deeper. We're asking whether infinity can exist in a physical way. We're asking whether the human mind evolved to understand rocks and rivers and trees, can even begin to touch a concept that defies logic and language. We're asking whether there's an end to the universe, and if there is, what happens if you go past it? Is there a wall, a void, a loop, or is past it simply not a valid question in a universe that has no outside? And then there's the problem of expansion itself. The rate at which the universe is expanding isn't slowing down as many scientists once assumed, it's speeding up. The space between galaxies is growing faster and faster, driven by a force we still don't understand, something we call dark energy, not because it's mysterious or ominous, but because it's invisible, unmeasurable. This means that the universe is not only unfathomably big, it's growing more unknowable with each passing second. There are galaxies that we can see now, whose light is reaching us from the distant past, but which are already retreating so fast that their future light will never reach us again. They are slipping over the cosmic horizon, never to be seen again, not because they're gone, but because they've become permanently unobservable. Imagine that, a universe that is not only bigger than we can comprehend, but actively erasing parts of itself from our reach, faster than we can record them. And yet here we are, a tiny species on a small blue planet, circling a middle-aged star on the outer arm of an average galaxy, asking questions that reach past the end of space and time. We build telescopes, launch probes, run computer simulations, and write equations that try to pin down something so large and so complex that even our best models are like finger paintings on the wall of an endless cave. But still we ask. Because asking is what makes us human. Because wonder is bigger than fear. Because every time we stare at the stars, we're not just looking outward, we're reaching, and in that reach, in that quiet, persistent need to understand what lies beyond the edge, we become part of the universe we're trying to measure. So how big is the universe really? Bigger than distance, bigger than numbers, bigger than time, maybe even big enough to hold all of our questions and still have room for more. Chapter 2. Is there a limit to what we can see? When you look up at the night sky, the light that meets your eyes is not simply brightness scattered across darkness. It's a record, a array of stories etched into photons that have traveled for millions, even billions of years to reach you. The twinkling of a star is not a present event. It is the past whispering through the silence. It is a memory stretched across space. And for as far as we can see, there is still one truth that wraps itself around every direction we look. We cannot see everything. There is undeniably a limit, a cosmic horizon beyond which light has not yet reached us, and perhaps never will. But this limit is not a wall. There is no solid boundary out there in space, no visible edge like a fence that tells us, beyond this line, the universe ends. Instead, the limit is something more subtle and more profound. It's a limit of time. Specifically, it's the limit of how far light has had time to travel since the beginning of the universe, which we believe occurred roughly 13.8 billion years ago in what we call the Big Bang. That number 13.8 billion years might tempt us to assume that the limit of our vision would also be 13.8 billion light years. But the truth is more astonishing than that. Because the universe has been expanding throughout that time, the actual distance to the most distant objects we can observe is much farther, currently estimated to be about 46.5 billion light-years in every direction, giving us an observable universe roughly 93 billion light-years across. It is vast beyond comprehension, yet still fundamentally limited. This observable sphere is called the cosmic light horizon, not because there's nothing beyond it, but because we are cut off from everything outside of it. Light from those outer regions simply hasn't had time to get here yet, and possibly never will. It's not that we're at the center of the universe. We are at the center of our own observable patch, just as every other observer in the cosmos would be at the center of their own. And each patch is limited by time, not geography. Think of it like standing in a vast foggy field, holding a flashlight. You can only see as far as the beam has traveled, and the field beyond remains hidden, not because it doesn't exist, but because light hasn't yet lit it up for you. Now imagine that fog isn't static. Imagine it stretching, expanding, while the light tries to reach it. That's our universe. That's the challenge we face when trying to peer past the horizon of the visible cosmos. But there's something else, something even more haunting. Because of dark energy, the force driving the accelerating expansion of the universe, some regions of space are not just unobservable for now, but unreachable forever. They are racing away from us faster than light, not because they are breaking the cosmic speed limit, but because space itself is growing between us and them. And since the speed of expansion increases with distance, it creates a terrifying reality. There are galaxies whose light we can see now, because it left them billions of years ago, but which are now moving away so fast that any future light they emit will never ever reach us again. They are not only beyond our present vision, they are beyond our future too. This means the cosmic horizon is not static, it's shrinking in a very real way. As time goes on, more and more of the universe slips beyond our reach, not because the galaxies themselves are dying, but because the universe is pulling the fabric of space so rapidly that communication between distant regions is being severed forever. In the far future, even the nearest galaxies may fade from view, leaving only the cold light of our own galactic cluster adrift in darkness. So when we ask whether there's a limit to what we can see, we're really asking two different questions. First, how far can light travel in the time since the universe began? And second, how much of the universe will still be visible to us as expansion accelerates? These aren't just technical concerns. They are profound limits on what we can ever know, ever map, ever measure. And it raises a philosophical question that cuts to the heart of human curiosity. If something exists, but no light from it can ever reach us, can we still say it's part of our universe? Is the universe what's out there, or is the universe defined by what can be observed, measured, and touched by consciousness? In a sense, every time a galaxy slips past the cosmic event horizon, it doesn't just disappear from view, it falls into silence, exiting the stage of our knowable reality. But there is another kind of limit, one we create ourselves. The telescopes we build, the detectors we design, the satellites we launch, they all have their own threshold. There is only so much resolution we can achieve, only so much clarity before the signal gets drowned in noise, in distortion, in interference from the Earth's atmosphere, or from the limitations of our instruments. The universe is generous with light, but we are still learning how to catch it, how to decode it, how to turn it into meaning. Every photograph from the Hubble Space Telescope, every infrared scan from the James Webb, every map of the cosmic microwave background is an attempt to stretch our eyes just a little farther, to bend that limit one more step outward. And even so, we may never truly know what lies beyond. Perhaps there are regions so alien, so wildly different from our cosmic neighborhood, that even if we could see them, we might not recognize what we're looking at. Perhaps physics itself changes out there. Perhaps galaxies form different. Perhaps there are forces, particles or patterns that we simply cannot detect from this far away, not because they are faint, but because they belong to a different part of reality altogether, cut off by the tyranny of distance, the geometry of space, and the relentless ticking of cosmic time. So yes, there is a limit to what we can see, but that limit is not fixed. It's a living boundary, constantly redrawn by light and time, by speed and gravity, by mystery and mathematics. It is a limit we press against, with every satellite, every equation, every theory and every question whispered into the night sky. And perhaps most importantly, it is a limit that reminds us of something fundamental, that knowledge itself has an edge, and that edge is not a wall. It is an invitation. Chapter 3. What lies beyond the observable universe? To imagine what lies beyond the observable universe is to step into a region of thought where measurement no longer serves us, where mathematics gives way to imagination, and where the very language we use to describe space begins to falter under the weight of what it cannot define. The observable universe, for all its grandeur and unfathomable scale, is not the totality of existence. It is only the part that light has revealed to us, the part that has had enough time to make itself known. But outside that glowing sphere, beyond that cosmic light horizon, there stretches a realm so vast, so hidden, and so silent that we may never touch it, not even in theory. And yet, we believe it is there. We are not guessing blindly. The structure of space, the uniformity of cosmic microwave background radiation, the distribution of galaxies across the sky, these aren't just data points. They are fingerprints of something much larger, much broader, much deeper than we can ever see. They whisper to us, not directly, but through subtle symmetry, through the way gravity shapes clusters of matter, through the smoothness of temperature variations, so perfectly balanced, it suggests a far greater stage than the one currently lit before us. When we speak of beyond the observable universe, we are not speaking of another world or some mythical land behind a curtain. We are speaking of more universe, more galaxies, more stars, more time, more distance, not in another dimension, but in this one, not hidden by magic, but by light, or rather by the lack of time for light to reach us. If we had more time, we might see farther, but time is not on our side. Expansion is outpacing illumination. So what is it like out there, in that invisible beyond? Is it more of the same? A continuation of the cosmic web, a never-ending grid of galaxies and dark matter, repeating patterns stretched across unimaginable distances? Or does something change once you pass the veil? Could there be a shift in the rules, a bend in the fabric, a glitch in the consistency of physics that only occurs once you step beyond our cosmic neighborhood? Some physicists propose that if the universe is infinite, then the space beyond our horizon must contain everything we have here, just rearranged in different configurations. Given enough distance, they argue, you might find a galaxy that mirrors our own, a solar system identical to ours, even an Earth with someone exactly like you sitting in a room just like this one, asking the very same question. It sounds absurd, fantastical, like science fiction whispered under the breath of mathematics, but in an infinite universe, even the improbable becomes inevitable. But others are not so convinced, because infinity is not a given. It is not proven. And even if the universe is truly infinite in size, we are still shackled by the limits of what can ever be observed. It's not just a matter of distance, it's a matter of accessibility. No information can ever pass from beyond that cosmic curtain into our instruments, into our equations, into our minds. The laws of physics don't merely make it difficult, they make it impossible. And yet impossibility has never been a wall for curiosity. It has always been a canvas. There are other ideas, stranger ones, bolder ones. Some theories propose that the universe beyond what we can see might be fundamentally different, that the constants we take for granted, gravity, electromagnetism, the mass of particles, The speed of light might vary beyond our visible bubble. If cosmic inflation occurred unevenly, if the early universe bloomed in patches, then each region might have frozen out with its own unique physics. In that sense, we could live inside a local pocket of laws, surrounded by alien bubbles, where the universe plays by different rules. This is the heart of the multiverse idea. Not a collection of alternate timelines, but a quilt of cosmic domains, each with its own identity, its own shape, its own destiny. These regions would be unreachable, unobservable, untouchable, and yet their existence could explain why our universe looks the way it does, why it seems so exquisitely fine-tuned for life, for structure, for meaning. Because in a sea of endless variation, only the pockets where conditions are just right would ever spawn stars, planets, and beings capable of asking why. But even without invoking the multiverse, there remains the core question: what's beyond the edge of what we can see? The simplest answer may be the most profound: more of the same. More stars, more galaxies, more dark matter shaping light into filaments and voids, more echoes of the Big Bang stretching endlessly into the dark. And if that's true, then the observable universe is not a special region. It's just the part of a much bigger whole that we happen to be able to witness for now. Still, that for now matters, because what we see today is not the full story. The universe is dynamic, not static. The light arriving now was emitted long ago, and what we see is a snapshot of the ancient cosmos. The galaxies we observe on the far edge of our visibility might no longer exist. They may have merged, evolved, or vanished into black holes, or they may have moved so far away that they have vanished into the unseeable. The present state of the universe beyond the horizon is not just hidden. It is unknowable in any real-time sense. This is not just a scientific limitation, it is a philosophical one. The universe beyond what we can see is a mirror of our own inner ignorance. It is a reminder that for all our brilliance, all our telescopes, all our models and measurements and dreams, we are still bound creatures, living in a bubble of light, surrounded by dark oceans of speculation. And yet we are not helpless. We may never touch what lies beyond the observable cosmos, but we can infer, we can map patterns, we can listen to the afterglow of creation, stretch it into data, and fold it into theory. We can simulate the birth of galaxies, follow the arc of inflation, model the geometry of space, and ask whether the whispers we hear in the background radiation tell the tale of a universe with no edge, no end, no center. Because even though we cannot see what lies beyond, we are not blind. We are imagining, and imagination, when shaped by evidence, becomes the sharpest tool science has ever known. So what lies beyond the observable universe? Perhaps everything. Perhaps nothing. Perhaps something we don't yet have words for. But whatever it is, it's not beyond wonder. Chapter 4. Could the universe be infinite? To speak of infinity is to speak of something that exists entirely outside our experience. The human mind, built to measure footsteps and lifespans, to track the passing of days and seasons, recoils at the idea of something that has no end. Infinity is not simply very big. It is not a number so large we cannot count it. It is the absence of boundary, of finality, of containment. And so, when we ask whether the universe might be infinite, we are not just asking about how much matter fills the void. We are questioning the very structure of space itself, and whether it ever stops, turns, loops, or fades. At first glance, the question seems almost unscientific. How can we ever know if something is truly infinite? How could we test it? How could we see to the end of something that by definition has no end? But physics doesn't need to walk the entire road to know if it curves. It doesn't need to visit the outer edge to know if the journey ever stops. Instead, it follows the laws, the ones that govern gravity, motion, energy, and light, and asks what shape of space those laws suggest. And so far, what we've seen is stunningly consistent. the universe appears on large scales to be remarkably flat. This flatness is not about how the universe looks in three-dimensional space, but how geometry behaves on a cosmic scale. In a flat universe, parallel lines never meet, triangles add up to 180 degrees, and the rules of Euclidean geometry hold firm. And if the universe is flat and continues to be flat beyond what we can see, then the most straightforward interpretation is that it extends forever. No curvature to wrap it into a loop, no positive bend to turn it into a sphere, just infinite, endless, uninterrupted space. But flatness alone does not prove infinity. Just as a flat piece of paper can be folded into a cylinder or looped into a torus, space might be flat and still be finite, if its topology is closed. That's what makes this question so subtle. Infinity and flatness are connected, but they are not married. You can have one without the other. So we look deeper. We search the skies for signs of repetition, for cosmic mirroring, for patterns in the cosmic microwave background that might suggest space loops back on itself. But so far, we've seen no such evidence. Every survey, every scan, every map suggests that the universe continues outward with no edge, no fold, no detectable repetition. But even here, we are limited by what we can observe, because just beyond our light horizon, the universe might bend. It might curve inward like the surface of a sphere, or loop back like a multi-dimensional pretzel. And because no information can reach us from those regions, we are left to infer, to model, to simulate, to wonder. It is a question not just of physics, but of scale. And at the scale of the entire cosmos, our certainty begins to blur. There are some who propose that the question itself may be flawed, that infinity might be a mathematical abstraction that does not exist in nature. After all, nothing in the physical world is truly infinite. We don't observe infinite energy, infinite density, infinite mass. Even black holes, which seem to contain singularities, are still surrounded by finite measurable regions. So why should space be the exception? Why should it go on forever when nothing else we know does? And yet others argue the opposite. They say that if the universe were finite, we might expect more signs, an edge, a wraparound effect, a cold spot or symmetry that reveals a closed topology. The absence of such clues might itself be a sign of infinity, like a shoreline that stretches beyond the horizon, not because we've mapped it, but because no bend ever shows itself in the waves. There is another way to consider the question, one rooted not in geometry, but in potential. If the universe is infinite in extent and also roughly uniform in matter distribution, then it must also contain infinite matter, infinite stars, infinite galaxies, infinite chances for every possible configuration of atoms to occur, including every possible configuration of. This is the uncomfortable heart of the infinite cosmos, that if it goes on forever, then somewhere out there, by the sheer force of probability, there is a version of you reading this same sentence in a room built from atoms, arranged almost but not quite, like your own. And this is not fantasy. It is not mysticism. It is cold statistical logic. In an infinite statistically random universe, duplication is not just possible, it is inevitable. Somewhere there may be another Earth, orbiting another sun, inside another galaxy, positioned 1 trillion light-years away, too far for light to ever bridge the gap, but real nonetheless. The sky may be littered not just with mystery, but with mirrors. But there is another view, one more grounded, more reserved. It reminds us that infinity is not required to make the universe amazing. Whether the cosmos is infinite or merely so large that it may as well be, the result is the same for us. We are confined to a bubble of observation, limited by the age of light, by the acceleration of space, by the reach of our tools, and whether the true answer is infinity or finitude, we may never know, because the boundary of knowledge is not the same as the boundary of space. The edge of what we can see is not the same as the edge of what is. Still, the question burns. Could the universe be infinite? Could it go on and on past every star, past every cluster, past every edge of what we can ever measure, ever dream, ever imagine? Could space be like thought, uncontainable, unending, expanding not only outward, but inward, into every atom, every question, every heartbeat that dares to ask? Maybe the universe is not infinite, but maybe the desire to understand it is. Chapter 5. Is the universe expanding into something or nothing? To understand what it means for the universe to expand, we must first unlearn almost everything we instinctively believe about how things grow. In the world we know, the world of objects, containers, surfaces and edges, expansion means pushing outward into something else. A balloon expands into the air. A city expands into the surrounding land. A ripple expands across the surface of a pond. In each of these there is always an outside, a space that existed before, waiting to be filled. And so, when we hear that the universe is expanding, our minds do what they have always done. They search for the outside. They ask, into what? What surrounds the universe? What is it pushing into? But the universe is not a balloon in a room. It is not a ripple on a pre-existing surface. It is not a thing inside something else, and that is where the difficulty begins. Not in the science itself, but in the limits of human intuition. Because space, as we know it, is not merely where things happen. It is one of the things that is happening, and its expansion is not the motion of galaxies flying through a static background. It is the fabric of space itself growing, stretching, unfolding with every second that passes. The expansion of the universe does not require a surrounding void. It does not need to spill into an external space, because there is no external space. There is only the universe itself. It is all that exists. It contains not just stars and matter and light, but space and time and dimension. When we say the universe is expanding, what we mean is that the distance between any 2 points in space, on large enough scales, is increasing, not because they are moving through space, but because space itself is growing between them. This expansion has no center. It has no edge. There is no cosmic boundary beyond which space begins, and no outer shell into which it spreads. It is everywhere uniform and all-encompassing, like the surface of a balloon being inflated, but not the balloon itself, because if we were to use that analogy properly, we would not be inside the balloon, but on its surface, living in 2 dimensions, unaware of any third. The surface expands, yet it has no center on the surface itself. Likewise, the universe expands, yet has no central point from which it does so, not from Earth, not from any galaxy, not from any hidden axis in space. So then the question returns, if the universe is expanding, is it expanding into something or into nothing? The most honest answer, strange as it may seem, is that it's not expanding into anything at all, because there is no outside of the universe, not in the physical sense. There is no space beyond space. There is no pre-existing emptiness for the cosmos to invade. What exists is what is. The universe is not pushing into a void. It is creating space as it grows. The expansion is not like an object moving through a room. It is like the room itself getting larger, with the walls drifting apart. Not because someone is tearing them down, but because the very metric that defines distance is changing beneath your feet. And yet this idea defies everything we've been taught about motion, about boundaries, about how things behave. We are used to space as the background, the canvas, the stage upon which events unfold. But in cosmology, space is not the stage. It is one of the actors, shaped and molded by the energy it contains. Einstein's general relativity showed us that space and time are not fixed. They bend, they stretch, they respond to mass and energy, they ripple when disturbed. And in the grandest scale of all, space doesn't just respond to energy, It evolves with it, grows with it, expands with it. When we say the universe is expanding, we are describing a change in the geometry of reality itself, not just a swelling of galaxies outward, but the deep rearrangement of how space itself is measured. And that expansion is not happening into something, it is all that is happening. But the mind rebels. It wants a container. It wants an answer that feels like a direction. An arrow pointing outward, past the edge of stars, beyond the edge of time. And so we ask, again and again, what lies outside the universe? What surrounds it? What is space expanding into? And the answer, again and again, is that the question may be meaningless, because the universe contains all of space. There is nowhere else to go. Still, there are other ways to explore the question. Some theories in cosmology propose that our universe may be part of a larger structure, a multiverse of many bubble-like domains, each with its own physical laws, each forming in a larger space-time landscape beyond our own. In such models, the expansion of our universe might take place within a grander metaspace, but even then we must ask, what is that expanding into? And so the question only grows deeper, folding into itself like an eternal loop. Because even in the most speculative theories, we never reach a true boundary, only a shifting horizon of description. So maybe the expansion is not about location, but about relationship. Maybe it's not about moving into somewhere, but about everything moving away from everything else, relative motion, on a cosmic scale, where there is no anchor, no center, no edge, just a web of shifting distances carried along by the momentum of the beginning itself. The Big Bang, then, was not an explosion in space. It was the birth of space. It happened not at a point in the universe, but everywhere in the universe, because there was no universe before it. There was no outside waiting, no place, no time, no space at all. The expansion that followed was not a ripple through the void. It was the creation of the void itself, stretched thin across a future that had never existed before. And so when we ask whether the universe is expanding into something or into nothing, we must make peace with the strangeness of the answer. The universe is expanding into itself, into a future it is constantly creating, into distances that did not exist a moment ago, into a silence that is not empty but pregnant with structure, with energy, with time. It is not expanding into anything. It is becoming everything. Chapter 6. Where is the center of the universe? It is perhaps one of the most natural questions a human being can ask when looking up at the stars. If the universe began from a single event, if all of time, space, matter and energy erupted in what we call the Big Bang, then surely there must be a place where it all began. A center, a point of origin. A cosmic location that can be marked, pointed at, named, even mapped. And if we could just find that place, maybe we could understand everything. But this question, like so many in cosmology, is not just difficult, it is built upon assumptions that do not survive the scale of the universe. Because despite how it feels, despite how every explosion we've ever witnessed has a point where it started and a direction it moves in, the universe is not expanding outward from a single location in space. It is not a fireball burning in the middle of a void. And the Big Bang was not a detonation that sprayed matter in all directions from a central origin. It was something far stranger, far more beautiful, and infinitely more difficult to picture. To say it plainly, the universe has no center, not in any meaningful physical way. And the reason for this lies in the nature of the Big Bang itself. The event we call the beginning of the universe did not occur in space. It was the birth of space. Space and time, as far as we can measure, did not pre-exist the Big Bang. They were born with it, which means there was no location where it happened, because there were no locations at all before it. There was no stage. There was only the moment of emergence, everywhere at once. This is perhaps the most difficult shift in perspective that cosmology demands of us, that we abandon our instinct to find the center, to locate ourselves relative to an origin, and instead accept that the expansion of the universe is not like matter flying away from an explosion in the air, but like the stretching of space itself, where every point is receding from every other and none holds a privileged position. Imagine standing on the surface of a balloon, not inside it, not outside it, on the surface, and imagine the balloon begins to inflate. You, along with thousands of tiny ink dots all around you, begin to move away from every other dot. No matter which direction you look, everything is moving away, and from your perspective, it might feel like you are the center of the expansion. But if another dot, on the other side of the balloon, made the same observation, they too would believe that they are at the center, and both would be right, because the surface is expanding everywhere, not from a single point, and there is no center on the surface itself. This analogy, though imperfect, captures the essence of cosmic expansion. We are not in the center of the universe, but neither is any other galaxy. Every galaxy sees other galaxies receding. Every point in space sees the expansion happening all around it. The entire universe, as far as we know, is homogeneous and isotropic on large scales, meaning it looks roughly the same in every direction, and has no special locations, no privileged axes, no cosmic bullseye. Even the cosmic microwave background radiation, the afterglow of the Big Bang itself, comes to us uniformly from every direction. We can detect slight ripples, minute variations in temperature that mark the seeds of galaxies, but no sign of an origin point, no sign of a directional burst. The universe is remarkably even, remarkably centerless, and yet the desire for a center persists. We want to be able to say that this is where it started, that this is the oldest part of the universe, that we are some specific distance from the beginning. But time, like space, began everywhere. There was no waiting room, no countdown in the dark. The Big Bang occurred not at a spot, but at every point. Every piece of the universe, no matter how far away, began at the same moment in cosmic time. And so, if we are looking for the center of the universe, the only true answer is everywhere. But that doesn't mean we are lost in randomness. The universe may lack a central point in space, but it is full of structure. Galaxies cluster along filaments, drawn together by gravity into shapes that resemble neural networks or spider webs, with vast cosmic voids in between. These formations are not symmetrical, not uniform on small scales, but they are patterns without a center, painted by gravity across an expanding canvas. And within that canvas, we find us, not at the middle of the universe, but at the center of our own observable one, the bubble of space from which light has had time to reach us since the beginning. Because of the finite speed of light and the age of the universe, we see ourselves surrounded by a sphere of information, a cosmic horizon centered on Earth. But this center is an illusion of perspective. Every observer, on every planet in every galaxy, is also at the center of their own observable universe. We are all in the middle, because the middle is everywhere. Some may ask, what if the universe is finite? Doesn't a finite universe require a center? But even then the answer remains the same. If space is curved back on itself, like the surface of a sphere in higher dimensions, then it can be finite without having an edge, without having a center. You could travel endlessly and return to your starting point, never finding a wall, never reaching the outside, and never crossing through a true middle. Just like walking around a planet, you'd find no edge, no center, only a loop. So we return to the question, where is the center of the universe? Not here, not there, not in any direction. The universe is not a thing expanding into something from a point at the center. It is a process, a flow, a shape in motion. The expansion is not directional. It is relational. It is the increase in distance between things, not their motion away from a source. The center of the universe is a myth born of small-scale intuition, scaled up to a cosmos where it does not belong. In truth, the center is nowhere. which means, in a way that is humbling and strangely beautiful, it is everywhere. Chapter 7. How do we measure a moving universe? In a world where everything is in motion, where galaxies drift apart and stars are born from swirling clouds of dust, how can we even begin to measure something as restless, as dynamic, as the universe itself? It is not enough to look up and say that the stars are shining. It is not enough to know that the galaxies are moving. To measure the universe is to measure not just position, not just speed, but the very shape and flow of space and time, the hidden metrics behind the cosmic dance. But unlike the things we measure here on Earth, objects we can touch, weigh, or enclose, the universe offers no solid boundaries, no external ruler, no stable platform from which we can step back and get the full picture. We are inside the thing we are trying to measure. We are woven into its fabric, moving with it as it expands. And so, to measure the universe, we must measure its motion from within, using the only tools we have: light, time, and gravity. The first great clue came not from telescopes or computers, but from a simple prism and a shifting line of color. When Edwin Hubble observed distant galaxies nearly a century ago, he noticed something astonishing. The light from those galaxies was stretched, shifted toward the red end of the spectrum. The farther away a galaxy was, the more its light was redshifted. It was as if the space between us and those galaxies was being pulled, like elastic, dragging the light into longer and longer wavelengths as it traveled. This effect, known as cosmological redshift, is not caused by the galaxies moving through space the way a car drives down a highway. It is caused by space itself expanding, while the light moves through it. And this discovery, so elegant, so powerful, allowed us to turn the sky into a map of motion. The more distant a galaxy, the faster it appears to recede. This relationship, known as Hubble's law, is the first step in measuring the universe's scale and speed. But redshift alone is only part of the picture. To truly measure the universe, we need to know how far things are. And distance, on cosmic scales, is not easy to measure. We cannot stretch a tape across millions of light years. We cannot send a probe across the void. Instead, we rely on standard candles, celestial objects whose intrinsic brightness we know well, like certain types of supernovae or pulsating stars called Cepheid variables. By comparing how bright they appear from Earth to how bright they should be, we can estimate how far away they are. It's a kind of cosmic triangulation, a subtle art of interpreting faint whispers of light across unfathomable distance. With each data point, each redshift, each standard candle, we begin to trace the outline of an invisible structure. We measure how fast the universe is expanding now and how that rate has changed over time. And what we've found is staggering. The expansion is not slowing down as gravity would suggest. It is speeding up, as if some unknown force is driving space apart with increasing urgency. We call this force dark energy, not because we understand it, but because we don't. It is not visible, not directly measurable. It does not clump like matter. It does not glow, and yet it makes up most of the energy content of the universe. By measuring how the expansion rate has changed over billions of years, cosmologists have been able to estimate the proportion of matter, radiation and dark energy in the cosmos, a remarkable feat of inference and precision built entirely from the faint echoes of light. And still the universe moves. It curves under the weight of its own gravity. It expands under the push of dark energy. It evolves, transforms, cools, and deepens. So we turn to another tool, one that reaches farther than any telescope: the cosmic microwave background. This ancient light, the afterglow of the Big Bang, is the oldest measurable radiation in existence. It has traveled for over 13 billion years to reach us, and in its gentle, uniform warmth, we find a map of the infant universe. Tiny fluctuations in the microwave background tell us how matter was distributed in those first moments, how dense, how smooth, how curved space was. From those fluctuations we measure not only the age of the universe, but its curvature, its rate of expansion, even its fate. And we do so not by looking outward, but by looking backward, back in time, back through layers of cosmic history frozen in light. Even time itself becomes a tool, because the farther we look, the older the light, the deeper into space, the deeper into the past. This gives us a kind of natural time machine, a way to observe not just how far galaxies are, but how they used to be. We can see the early universe as it was when it was just forming stars. We can see how structures assembled over time, how galaxies grew, how voids expanded, how the universe changed its tempo as it aged. And from this dance, this redshift, this brightness, this ancient light, we build models, we write equations, we simulate the past and project the future. We use general relativity to understand how space bends under mass, and we use quantum mechanics to understand the particles that populate that space. We use geometry to measure curvature, we use thermodynamics to measure entropy, and we build a story, a moving, breathing story that changes with every new observation. But even here in this symphony of precision and data, we must be cautious, because the universe is not just moving, it is moving in ways we may not fully understand. There may be forces we haven't discovered, dimensions we cannot detect, principles we have not yet imagined, and every measurement we make is filtered through the lens of our current knowledge, our current tools, our current place in the cosmos. And so to measure a moving universe is to chase a horizon that always runs ahead. It is to draw maps in shifting sands. It is to read the future in ancient light. And it is to accept that even our best numbers are not final truths, but approximations, beautiful, precise, and incomplete. Yet we measure anyway, because each calculation brings us closer. Each signal, each wavelength, each flicker of a distant supernova adds a new pixel to the portrait. We are not standing still, looking out at a moving world. We are inside the motion, part of it, measuring not from the outside, but from within. And that makes every measurement more than just data. It makes it a message, from the universe to itself. Chapter 8. Can space itself stretch forever? To ask whether space can stretch forever is to confront the very nature of reality. Not the things within space, but space itself. The quiet, unseen scaffolding that holds all galaxies, all atoms, all light, and all time. We so often treat space like an invisible box, a background against which the story of the universe unfolds, passive and still. But in truth, space is not still. It is not quiet. It is not a container. Space is dynamic, elastic, and profoundly alive in ways that defy our everyday experience. And when we speak of the universe expanding, what we are truly describing is space itself, stretching, not into something, but stretching in its very being, expanding from within, carrying all of existence along with it, like a current that flows not through space, but as space. But how far can this stretch go? Could space continue expanding endlessly, eternally, without boundary or end? Could it, in some unknowable future, reach such vastness that even the word infinite feels too small? To answer, we must first understand that space is not a passive stage. It is shaped and sculpted by energy and mass. It warps around stars. It curves around black holes. And at the scale of the universe, it swells and stretches in response to the sum total of everything within it. Space is not something separate from the matter it contains. It is inextricably intertwined with energy, time, and gravity. At the heart of this expansion is a phenomenon we still do not fully understand, the accelerating force known as dark energy. This mysterious component, which makes up nearly 70% of the universe's energy content, is not pushing galaxies through space like wind through sails. It is causing space itself to expand faster and faster over time. And unlike gravity, which weakens with distance, dark energy's effect seems to be constant or even increasing, accelerating the growth of the cosmos in a runaway expansion that has no known limit. If this acceleration continues, and all current measurements suggest that it will, then the future of space is one of eternal expansion. Galaxies will recede beyond the limits of visibility. Clusters will be torn apart. The cosmic web will unravel. Eventually, only the dim light of local stars will remain, flickering in a sea of emptiness that grows colder and darker with each passing eon. In such a future, space will not stop expanding. It will stretch forever, not because there is something forcing it outward, but because the very geometry of the universe is governed by rules that make expansion the path of least resistance. The equations of general relativity, when applied to a universe with dark energy, show that space can and will continue to grow unless acted upon by an opposing force, but there is no such force. The universe is not resisting expansion, it is surrendering to it. And this leads us to a haunting possibility, that no matter how far space stretches, it may never reach a limit, because there may be no limit to reach. There is no edge of space waiting out there. There is no outer boundary, no cosmic wall, no edge of the map beyond which space cannot stretch. Expansion does not push space into something else, it creates more space. It generates the very distance that separates things. And so space could stretch forever, not into a pre-existing void, but into itself, endlessly rewriting its own fabric. But forever is a heavy word. Can anything truly continue without end? Does infinite expansion require infinite energy, or will there come a time, far beyond any star or memory, when the stretching slows, stalls, or transforms into something else? There are cosmological models, some speculative, others supported by partial evidence, that suggest possibilities beyond eternal expansion. Perhaps dark energy will change over time. Perhaps it is not constant, but evolve. In some scenarios, the force that now causes space to stretch could reverse, collapsing the universe in a big crunch, a mirror image of its beginning. In others, expansion could accelerate so violently that space is torn apart in a big rip, destroying galaxies, stars, planets, atoms, even the fabric of space and time itself. But the current consensus, based on everything we can observe, is that expansion is not slowing, it is speeding up, and that speed, that cosmic inflation, may never stop. Still, we are not powerless in the face of infinity. We do not need to reach the end of something to understand how it behaves. We do not need to see the final page of the story to understand the arc of its narrative. Through observation, through theory, through relentless curiosity, we can map the course of space, measure its curvature, chart its growth, and estimate its future. And what we find again and again is that space is not just stretching, it is compounded. The farther away something is, the faster it appears to recede. This means that beyond a certain distance, galaxies are already moving away from us faster than the speed of light. Not because they are breaking cosmic laws, but because the space between us is expanding so rapidly that light can no longer bridge the gap. These galaxies have already slipped beyond our horizon. Their light will never reach us. They exist beyond the veil, in a universe that is still ours, but forever out of reach, and more will follow. Every second, more of the cosmos is lost to distance, more of the night sky slips into darkness, not because it is ending, but because it is running away, or rather, because space itself is running away from itself, creating more of what it is in every direction, without pause, without sound, without edge. So can space itself stretch forever? Yes, if the current laws of physics remain as they are. Yes, if dark energy continues to dominate. Yes, if expansion is not merely a phase, but the fundamental trajectory of reality. And even if not, even if one day expansion ceases, even if one day a new force bends space back inward, or transforms it into something else entirely, that change will not erase the stretch that has already happened. It will not undo the centuries of light, the billions of years of cosmic drift, the tapestry of galaxies flung outward like sparks from a fire that never stops burning. The universe is not moving through space, it is the movement of space itself, and that movement, gentle, silent, relentless, may be the longest story ever told. Chapter 9. How did the universe get so vast in so little time? It is one of the most astonishing facts in all of science that within a tiny fraction of a second after the birth of the universe, space itself underwent an expansion so rapid, so violent, so wildly beyond anything we experience in the physical world, that it defies both our intuition and our ability to fully imagine it. The universe, which at the very beginning may have been smaller than a single atom, expanded to a size many orders of magnitude larger in far less time than it takes for a beam of light to cross the head of a pin. And somehow, within this moment of unimaginable speed and silence, the foundation was laid for every galaxy, every star, every world, every breath, and every question that would ever come. This event is known as cosmic inflation, and it is one of the most extraordinary and important ideas in modern physics. Not because it is easy to understand, but because it solves a puzzle that stares at us every time we look up into the night sky and see the same patterns, the same smoothness, the same temperature stretching across the entire universe. The puzzle is simple to ask, but staggeringly complex to explain. If light travels at a finite speed, and if the universe is only about 13.8 billion years old, then how can opposite sides of the cosmos, regions that are over 90 billion light-years apart, look almost exactly the same? How can the temperature of the cosmic microwave background, the afterglow of the Big Bang, be nearly identical in every direction, down to 1 part in 100,000, if there was never enough time for those distant regions to exchange light, information, or energy? This problem, known as the horizon problem, forced physicists to rethink the very early universe, and the solution they proposed was as bold as it was beautiful. What if the universe wasn't always expanding at the rate we see today? What if, in its earliest instant, it expanded faster than the speed of light, not by violating physics, but because the rules of space-time themselves allowed it? Inflation theory proposes that just after the Big Bang, the universe experienced an exponential expansion, driven by a high-energy field permeating space. In less than a trillionth of a second, space itself doubled in size not once, but dozens of times. This kind of growth is not merely fast, it is incomprehensibly fast, a speed so great that regions of space that were once microscopically close were pulled apart to cosmic distances almost instant. And in doing so, inflation stretched the initial irregularities, the quantum fluctuations, the tiniest differences in energy and density at the quantum scale, into the seeds of galaxies and galaxy clusters. What was once chaos at a subatomic level became the structure of the universe. The noise became the music. The randomness became the scaffold of everything. This idea, outrageous as it may sound, is supported by observation. The patterns we see in the cosmic microwave background, the temperature variations, the scale of clumping, the statistical distribution of hot and cold spots, match what inflation predicts. The flatness of the universe, the smoothness of its structure, the absence of magnetic monopoles, the incredible uniformity across vast distances, these are not random coincidences. They are precisely the kind of fingerprints left behind by a burst of cosmic inflation. But this brings us to the deeper question: how did the universe become so vast in so little time? The answer lies not just in speed but in scale. Inflation did not move matter through space, it expanded space itself, taking every point and pulling it away from every other, creating more and more distance with every passing fraction of a second. This is not like an explosion, where particles fly outward into emptiness. It is like the stretching of a fabric that brings distance into being, not by moving things but by changing what distance even means. This is why inflation can outpace the speed of light without breaking relativity. Objects within space cannot move faster than light, but space itself can expand at any rate it wants. And during inflation it did. The fabric of reality surged outward in a cosmic blink, faster than any signal, faster than any cause could chase its effect, faster than imagination itself. And when inflation ended, when that strange energy field decayed into the particles and forces we know today, it left behind a universe filled with hot, dense plasma, ready to cool, condense, and begin the long, slow process of becoming stars, galaxies, and worlds. But the space had already been set, the size had already been imprinted, the vastness had already taken hold. What's even more mind-bending is that inflation might not have been a one-time event. Some models suggest that inflation never truly ends. It just slows down locally in pockets of space, like the one we live in. In other regions, it continues forever, spawning new universes with every passing moment, each one bubbling off from the inflating background like sparks from a cosmic fire. This is the idea of eternal inflation, and it suggests that the incredible size of our universe is not unique. It's just one of countless others, all born from the same expanding sea. But even if our universe is the only one, its size remains staggering. Galaxies billions of light-years apart, clusters of galaxies forming structures that span hundreds of millions of light-years, cosmic voids so large that entire galaxies would disappear inside them without a trace. And all of it, the structure, the smoothness, the scale, was written into the fabric of reality within the briefest instant after the beginning. So how did the universe get so vast in so little time? It didn't grow like a tree grows, one branch at a time. It didn't spread like water across a floor. It erupted into scale, driven by forces we are only beginning to understand, governed by equations we are still refining, witnessed by light that took billions of years to reach our eye. And that vastness, the silent immensity of it, is not something separate from us. We are part of it. We live inside the consequence of that early expansion. Our atoms were born in the stars that formed because of that first. Our thoughts are shaped by the time and space that inflation carved into being. And our questions, our wonder, are the echoes of a universe that got impossibly big, impossibly fast, and left us here to ask why. Chapter 10. What does size mean in a curved cosmos? In our everyday world, the idea of size seems so simple, so concrete, so obvious that we rarely stop to consider what it means. We measure the length of a room, the diameter of a circle, the width of a river. We stretch a ruler across a surface and assign numbers to the space it covers, believing we are capturing something objective, something permanent. But this understanding begins to falter, quietly at first, and then completely, when we leave the world of straight lines and flat surfaces behind and step into the geometry of the cosmos itself. Because out there, in the depths of space and time, size is not absolute. It is not fixed. It is not something that remains the same no matter who is measuring or from where. In the curved universe we inhabit, space does not simply extend outward in all directions like a calm ocean. It bends, it folds, it stretches and contracts in response to gravity, to energy, to the very presence of mass. And when space is curved, the idea of how big something is becomes a question without a single answer. To understand this, imagine walking across the surface of a massive sphere, like a planet. If you set off in one direction and never turn, eventually you'll return to where you started. From your perspective, the journey was straight, uninterrupted, infinite in one sense, and yet looped in another. And if you were to measure the distance between 2 points using a rope stretched across the surface, your result would differ from what you'd get if you could measure straight through the sphere instead. On a curved surface, distance depends on the path you take, and in space, those paths are determined not by preference, but by gravity and geometry. Einstein's general theory of relativity tells us that mass and energy curve space-time, and that everything, including light, must follow the curvature of this fabric. So, when we look into space and measure how far away a galaxy is, we are not measuring a straight line through some absolute void. We are measuring along the curves, through the distortions, across the warps of space-time. The route the light has taken may not be the shortest, and the scale we apply may stretch or shrink, depending on the observer, the method, and the era in cosmic history. And this curvature is not just local. On the largest scales, the universe itself can have curvature, not the kind caused by individual stars or galaxies, but the overall shape of space itself. Cosmologists speak of 3 possibilities: a universe with positive curvature, like the surface of a sphere; a universe with negative curvature, like a saddle bending away at every point; and a universe that is flat, with no overall curvature, like an infinite sheet of paper. Each of these shapes affects what size means in radically different ways. In a positively curved universe, space is finite, but unbounded, meaning it wraps around itself. You could travel in a straight line forever, and eventually end up where you began. In such a universe, the total size is measurable, but not by any conventional edge. There are no walls, no borders, no stopping point, just a looped geometry that turns endless motion into a closed journey. In a negatively curved universe, space is open and infinite, expanding in all directions, but bending in such a way that parallel lines diverge, and the angles of triangles add up to less than 180 degrees. This kind of universe has no boundary and no looping. It stretches forever, not with symmetry, but with an ever-widening hunger for distance. And in a flat universe, the one our measurements currently favor, space is both infinite and uniform. Parallel lines remain parallel. Geometry behaves as we learned in school, and yet, even in this apparent simplicity, the expansion of space and the relative nature of distance still make size a concept that depends heavily on when and how you measure it. Because size in the universe is not just a matter of length, it is also a matter of time. When we say a galaxy is 10 billion light-years away, we mean that the light we are now receiving from it has traveled 10 billion years through space. But that galaxy is not located 10 billion light-years away now, because the universe has expanded in the time since the light left. The galaxy's current distance may be more than twice that, 20 billion light-years or more. So even the simplest question, how far away is it, splits into multiple answers: distance when the light was emitted, distance as measured by redshift, distance now, distance light has traveled. In a curved, expanding universe, these are not the same. And then there is the question of volume. How large is the universe as a whole? If space is curved, then the volume enclosed within a certain radius may be more or less than what simple formulas would suggest. In a positively curved space, you can draw a sphere of a given radius and find that the volume it contains is less than expected. In a negatively curved space, it will be more. Even the rules of area and circumference begin to unravel. A circle drawn in curved space does not behave like one drawn on a chalkboard. Its perimeter, its area, its angles, all shift with the shape of the space it inhabits. This is not theoretical abstraction. We see the effects of curvature in gravitational lensing, where light from distant galaxies is bent by the gravity of massive clusters. We observe the warping of time near black holes, where seconds stretch into centuries, depending on where you stand. The very path of starlight, the structure of cosmic filaments, the patterns of microwave background radiation, all whisper the same message. Space is not flat, not completely, not everywhere, and the idea of size must be flexible enough to live within that truth. So when we ask what size means in a curved cosmos, we must let go of the comfort of rulers and measuring tapes. We must embrace a deeper kind of measurement, one rooted in relativity, in light paths, in curvature, in time. We must measure the shadows that distances cast, the echoes that travel across bending corridors of space, the red-shifted signals of galaxies we will never touch. And in doing so, we find that size is not a simple number. It is a relationship, a map that changes depending on where you are and how you move. It is not something the universe has. It is something the universe becomes, moment by moment, stretch by stretch, as space flows outward into its own unfolding form. In a curved cosmos, the idea of size is not lost. It is just more mysterious, more profound, more alive. Chapter 11. Could the universe wrap around itself like a loop? When we imagine the universe, we often imagine it expanding outward into some vast and boundless emptiness, endless stars drifting farther and farther apart, galaxies carried on a current of ever-growing space, all of it heading into the infinite, with no direction and no destination. But there is another possibility, one stranger and more subtle, a shape that bends instead of breaks, that folds instead of flies, that stretches not into forever, but into itself. And the question it poses is this: what if the universe wraps around itself? What if it loops, curls, or closes, not with an edge but with a twist? This is not science fiction. It is a serious question in modern cosmology, rooted in geometry, guided by evidence, and shaped by the principles of general relativity. Because space, like light, like time, does not have to behave in ways our eyes expect. It can be curved, it can be compact, it can be finite without having borders. Just as the surface of the Earth allows you to travel forever in one direction and eventually return to where you began without ever falling off the edge, the universe may also possess such topological elegance on a scale far beyond anything we can directly perceive. This idea begins with curvature. Einstein taught us that mass and energy warp the fabric of space-time, but even without matter, the universe can possess an intrinsic shape. It can be positively curved, like the surface of a sphere, negatively curved, like a saddle, or flat, like an infinite plane. These are not just abstract categories. They determine how space behaves, how distances are measured, how parallel lines move, how the universe evolves over time. But beyond curvature lies topology, the true architecture of space, the way it is connected, the way it might loop or fold in higher dimensions, the way it might close without ever needing an edge. If the universe has a closed topology, then it could be finite in volume, while still having no boundary, no edge where you would fall off, no wall to crash into, just a seamless continuity that leads you back to where you started. You could, in theory, travel in one direction forever and return to your point of origin, having looped around the cosmos in a path that bends without your ever noticing. And such a universe would not appear any different in the short term. It would look to us like an endless expanse. But subtle signs might remain: patterns in the background radiation, repeated structures in the sky, symmetry on a scale so vast it escapes our first glance, but not our instruments. Cosmologists have searched for these signs. They have studied the cosmic microwave background, the relic light of the Big Bang, for repeating circles, for anomalies that might suggest we are seeing the same region of space in different directions. If the universe is small enough to loop within our observable bubble, there might be overlapping light paths, mirrored galaxies, multiple images of the same ancient structures. So far, no conclusive evidence has been found. The data favors a universe that is at least larger than the region we can observe, and possibly infinite. But the absence of proof is not proof of absence. The loop may simply lie beyond our light horizon, beyond our ability to. But even if we cannot yet prove that the universe wraps around itself, the idea still opens a door to a way of thinking that changes everything, because a looping universe is not just a shape, it is a concept. It tells us that size is not the same as extent, that infinity is not the only form of boundlessness, and that the cosmos may be self-contained in ways we are only beginning to imagine. It tells us that out there might eventually lead back to here, that the straightest possible path could be a circle, that the map of everything could be a closed loop with no beginning and no end, and there are even more complex topologies to consider beyond simple spheres or tori. Space could be multiply-connected, like a hall of mirrors in higher dimensions, where light wraps and twists and returns, not in a circle but in a spiral or a Mobius-like reversal. The universe could be shaped like a three-dimensional torus, a kind of cosmic donut where every axis loops, or it could be a more exotic manifold, a shape we cannot visualize but can describe mathematically, where paths reconnect in ways that defy our three-dimensional instincts. These ideas are not just academic curiosities, they have real implications. In a looping universe, there is no preferred direction, no favored center, no special edge. Everything is connected, every path eventually closes, even time perhaps could follow such a path, cycling, returning, flowing in ways we cannot yet detect. Some speculative theories suggest that the universe might oscillate, that the Big Bang was not a one-time event, but one loop in a greater cycle of expansions and contractions, beginnings and endings tied together by the fabric of space itself. But here, once again, we face the limits of observation. We can only see so far. We can only measure what light has had time to reach us. And if the loop is bigger than our horizon, if the universe wraps around itself only beyond what we can observe, then we may never find the evidence we need. We may live our entire existence within one small patch of a looping hole, unable to see the larger pattern from inside the thread. And yet the beauty of the idea remains. That space may not simply go on forever, but reconnect with itself, enclosing all things within a grand curved symmetry. That the universe may be finite, but unbounded. That the journey outward may also be a journey inward. That what we call distance is not a straight line, but a path that always leads us home. So could the universe wrap around itself like a loop? Yes. Mathematically, geometrically, even philosophically. It is not only possible but elegantly consistent with the laws of relativity and the shape of space. Whether it does is still uncertain, but the idea invites us to see the cosmos not as a road that vanishes into infinity, but as a circle that folds back upon itself, quietly, invisibly, infinitely mysterious. And in that folding perhaps lies a truth more profound than infinity. A universe with no edge, no center, and no end. Only return. Chapter 12. Is the universe flat, closed, or open? And why does it matter? If you could step outside the universe, if you could rise above it somehow, looking not at its contents but at its shape, at the underlying architecture that holds it all together, what would you see? Would the cosmos extend endlessly in every direction, a flat, infinite plane with no edge and no center? Would it curve gently around itself like the surface of a sphere, forming a closed, finite hole with no boundary? Or would it stretch out like a saddle, forever open, forever expanding, curving outward with no return? These are not idle questions. They are not abstract games of geometry. They are the very framework of everything, the fabric of reality, the shape of space, the destiny of the cosmos itself. In cosmology, when we speak of a universe that is flat, closed, or open, we are not speaking about the contents of the universe, the stars, the galaxies, the matter and energy, but the geometry of space itself, the way it bends and stretches under the influence of gravity and expansion. This shape, known as spatial curvature, is determined by the total amount of energy and matter in the universe, and it governs how the universe behaves at the largest scales, how light travels, how time flows, how distances relate to each other, and ultimately what the fate of the universe might be. A flat universe follows the familiar rules of Euclidean geometry, the geometry we learn in school, where parallel lines never meet. The angles of a triangle always add up to 180 degrees, and the shortest distance between 2 points is a straight line. In a flat universe, space is not curved overall, though it may still be warped locally by massive objects like stars or black holes. And crucially, a flat universe can be either finite or infinite, depending on its topology. It may go on forever in all directions, or it may loop around itself in subtle ways we cannot yet detect. A closed universe, by contrast, is positively curved, like the surface of a sphere. In this geometry, parallel lines eventually converge. The angles of a triangle add up to more than 180 degrees. And if you travel far enough in a straight line, you might eventually return to your starting point. A closed universe has finite volume, but no boundaries. There is no edge, no wall, no outside. It is a self-contained whole, looping back into itself, a cosmic echo of completeness. An open universe, on the other hand, is negatively curved, like a saddle or a sheet bent outward in all directions. In this geometry, parallel lines diverge, and the angles of a triangle add up to less than 180 degrees. An open universe is infinite, ever expanding, with a curvature that grows more pronounced the farther you go. It spreads like ripples in a boundless pond, never closing, never returning. So which of these is our universe? For decades, astronomers and physicists have turned their instruments to the sky in search of an answer, using light, gravity, and geometry itself as their guide. They have studied the cosmic microwave background, the oldest light in the universe, with exquisite precision, mapping its temperature fluctuations across the sky, searching for the subtle signatures of spatial curvature written into its ancient glow. And what they have found, again and again, is something remarkable. The universe appears to be flat. Not perfectly flat, perhaps, but so close to flat that any curvature must be extremely slight, on scales we have not yet been able to measure. This observation has profound implications, because in general relativity, the curvature of space is directly tied to the density of the universe, not just the density of visible matter, but of all matter, all radiation, all dark energy. A flat universe means that the total energy density equals what is known as the critical density, the precise balance point between collapse and runaway expansion. If the density were higher, the universe would be closed, curved like a sphere, and destined to recollapse in a big crunch. If the density were lower, the universe would be open, expanding forever, but in a geometry that diverges endless. But at the critical density, space is flat. Expansion continues forever, but ever more slowly, like a stone thrown just hard enough to escape a planet's pull, drifting endlessly toward infinity without ever truly escaping gravity's grasp. And yet, this balance is fragile. For the universe to be this close to flat today, it must have been even closer in the past, so precisely tuned in the first moments after the Big Bang that the difference between a flat and a curved cosmos would have been less than 1 part in 100,000 trillion. This extraordinary fine-tuning is one of the puzzles that gave rise to the theory of cosmic inflation, the idea that in its first instant the universe expanded so rapidly that any initial curvature was flattened out, like the surface of a balloon stretching smooth as it inflates. So why does any of this matter? Because the shape of space is not just an abstract property. It determines how light travels over great distances, which in turn affects what we see. It determines how structure forms, how galaxies cluster, how voids stretch, how the fabric of the universe grows and bends. And most of all, it determines the ultimate fate of everything. In a closed universe, expansion would eventually slow, halt and reverse. Galaxies would stop receding, then begin to draw closer. A space collapses in on itself. Stars would drift into darkness, time would reverse its arrow, and the universe would end as it began, in a singularity of unimaginable density and heat. In an open universe, expansion would never stop. Space would grow thinner and colder. Stars would die. Galaxies would recede into invisibility. The sky would go dark, and the universe would fade into heat death, a vast, empty stillness, with no warmth, no light, no memory. In a flat universe, the outcome is more delicate. Expansion continues forever, but the rate slows, balancing on the knife edge between collapse and flight. Over trillions of years, stars still burn out, matter still decays, but the end is neither crash nor explosion, it is silent. And so we return to the question, quiet but urgent, is the universe flat, closed, or open? The evidence says flat, but with room for mystery, room for new measurements, new revelations, new truths we have not yet imagined. And in that mystery lies a kind of poetry, because the shape of space is not something we see directly. It is something we feel through observation, infer through light, trace through time. It is the shape of everything, not just of where we are, but of what is possible. To ask the shape of the universe is to ask about beginnings, about endings, about whether the road leads home or vanishes forever. It is not just geometry. It is the question of where we are in all of existence, and where, if anywhere, it leads. Chapter 13. How do we know the universe is still expanding? To say that the universe is expanding is to say that space itself, the very framework in which all things exist, is growing with every passing moment, and that the distances between galaxies are not just increasing because of their own motion through space, but because the space between them is literally stretching. It is not a theory born of wishful thinking or poetic metaphor. It is a conclusion rooted in light, in data, in silent signals traveling billions of years through the vacuum to arrive at our fragile instruments. And it is a conclusion that continues to be confirmed, over and over again, with greater precision, with deeper reach, with quieter awe. But how do we know? What tells us that the universe is still expanding? Even now, even as we speak, even as stars flicker out and galaxies drift into silence. The first clue came not from distant galaxies, but from a shifting light, a phenomenon known as redshift. When Edwin Hubble observed the light from distant galaxies in the early 20th century, he discovered something both elegant and shocking. The light was stretched, its wavelengths elongated, its spectrum shifted toward the red end. And the farther away the galaxy, the more its light was redshifted. This was not simply the Doppler effect, the way a siren changes pitch as it moves past. It was something far more profound. It meant that space itself was stretching, while the light traveled, pulling the wavelengths longer and longer as they moved through the expanding void. This relationship, now known as Hubble's law, was the first piece of evidence that the universe was not static, not eternal and unchanging, but dynamic, evolving, in motion. It told us that galaxies were not simply scattered through an empty void, but were being carried apart by the expansion of the very stage they occupied, and that expansion was not limited to the past. It was and is ongoing. But a single snapshot is not enough. To know the universe is still expanding today, we need more than historical redshifts. We need to look across time, across space, across billions of years of light, and see whether the pattern continues, not just whether galaxies are redshifted, but whether the rate of redshift itself evolves. And that is exactly what astronomers have done. Using powerful telescopes, both ground-based and orbital, scientists have observed supernovae, specifically Type 1a supernovae, the thermonuclear explosions of white dwarf stars in binary systems. These events are extraordinarily bright and occur with consistent luminosity, making them excellent standard candles for measuring cosmic distances. By comparing the apparent brightness of a supernova to its intrinsic brightness, we can calculate how far away it is, and by analyzing its spectrum, we can measure its redshift, how much space has stretched since the light was emitted. When these measurements are plotted for supernovae at different distances, that is, different points in cosmic history, they reveal something astonishing. Not only is the universe expanding, but it is expanding faster now than it was in the past. This acceleration is one of the most important discoveries in all of cosmology, and it reshaped our understanding of the universe at the deepest level. We had once assumed that gravity, the force pulling everything inward, would gradually slow the expansion. But what we found instead was that some mysterious force, which we now call dark energy, is acting in the opposite direction, pushing galaxies apart, driving the expansion to ever greater speeds. This revelation does not come from speculation. It comes from light, from measurement, from the careful observation of distant explosions that occurred billions of years ago, and whose photons are only now reaching our detector. It comes from the pattern of galaxies across the sky, from the ripples in the cosmic microwave background, from the large-scale structure of the universe itself. Every line of evidence, every map of cosmic growth, every survey of the night sky tells the same story. The universe is not only expanding, it is doing so at an increasing rate, and we are still watching it happen. Every year, new instruments refine our view. The Dark Energy Survey, the Planck satellite, the Euclid mission, the James Webb Space Telescope. Each of these tools reaches deeper into the past and further into the present, revealing not just the layout of galaxies, but the history of expansion written in the stretching of space and the cooling of ancient light. With each observation, we are watching the universe breathe, slowly, silently, but undeniably, its fabric continuing to stretch in all directions. We also detect expansion through baryon acoustic oscillations, subtle imprints of sound waves in the early universe, frozen into the distribution of galaxies. These patterns act like a cosmic ruler, allowing us to measure how distances change over time. And once again, the result is the same. The ruler is growing. Space is expanding. The scale of everything is shifting outward. But perhaps most compelling is the simplicity of the idea once it is understood. If the universe is expanding, and has been since the Big Bang, there is no reason to assume it suddenly stopped. All the forces that were present then are still present now. All the dynamics that governed early expansion still apply, and every observation we make confirms this. Expansion is not a phase. It is a property of space itself, a behavior encoded in the laws of general relativity and visible in the very photons that bathe our instruments every night. So how do we know the universe is still expanding? Because light tells us so. Because time tells us so. Because the galaxies are not staying still. Because space is not static. Because the math works. The measurements agree, and the sky whispers it in every direction we choose to listen. Because the very structure of what we see, the distances, the redshifts, the stretching of waves across the void, can only be explained if the universe is not done growing, and perhaps it never will be. Chapter 14. Why is the universe getting bigger faster? When we first learned that the universe is expanding, it was as though the heavens had breathed for the very first time. A revelation that space was not a fixed stage, but a living, moving field, growing between galaxies, stretching quietly with time. And for a while, that idea was enough. The cosmos was getting bigger. Yes, but surely gravity, the gentle pull of every atom on every other, would act as a brake, slowing the expansion, dragging everything back together, or at the very least, keeping the stretching in check. The universe would expand, then slow, perhaps stop, perhaps fall back inward. That seemed logical. That felt right. But nature is not bound by what feels right, because when we began to look more closely, when we began to measure, not just that space was growing, but how fast, and how that speed changed over time, we discovered something that shattered those expectations. The expansion of the universe is not slowing down, it is speeding up, and this acceleration is not slight, it is not subtle, it is a runaway growth, a swelling of space itself that becomes more dominant with each passing eon, pushing galaxies away from one another faster than they were yesterday, and faster still tomorrow. The question is no longer whether the universe is expanding, it is why this expansion is accelerating. What force, what energy, what hidden hand is driving the cosmos apart with increasing urgency? To understand why this is so strange, imagine tossing a ball upward. Gravity pulls it back. If you throw it hard enough, it may escape Earth's grip and fly off into space. But even then, it will slow as it climbs. That's what we expected of the universe, a big bang that hurled matter outward, and gravity pulling back. But what we found instead was like throwing the ball upward, and watching it speed up as it rises, racing away faster the farther it gets, as if some invisible engine were hidden in the sky. This invisible engine has a name: dark energy. It is called dark, not because it is sinister or shadowed, but because it is unknown. It does not emit light, it does not absorb light, it does not seem to clump like matter or form structures like galaxies. Yet it makes up nearly 70% of the total energy in the universe, and its effect is not localized. It is everywhere, woven into the very fabric of space itself. In fact, dark energy is space. Or rather, it is a property of space, something inherent in its nature, something that exerts a kind of negative pressure, pushing rather than pulling, accelerating rather than decelerate. When Einstein first formulated general relativity, he included a term known as the cosmological constant, a small energy associated with empty space, meant to counteract gravity and allow for a static universe. Later, when expansion was discovered, he called it his greatest blunder and removed it. But as it turns out, the universe did not stand still. It grew. And not only that, it grew fast. Einstein's blunder may have been a glimpse of the truth that space is not merely an empty backdrop, but a source of energy in its own right, capable of driving cosmic acceleration. Modern measurements, especially of distant supernovae, the cosmic microwave background, and the large-scale structure of the universe, confirm that this acceleration is real. Galaxies billions of light-years away are receding faster than galaxies closer to us. And when we compare the rate of expansion today to that in the ancient past, we see the curve bending upward, the acceleration increasing. But what exactly is dark energy? That remains one of the greatest mysteries in all of physics. Some believe it is a true cosmological constant, an unchanging energy density of the vacuum present everywhere, always. Others believe it is a dynamic field, something that changes with time and space, something that evolves, perhaps called quintessence, a fifth element beyond matter, radiation and gravity. And still others think that maybe we don't understand gravity as well as we thought, that maybe at cosmic scales the equations bend, and the universe behaves in ways we have yet to imagine. But regardless of what dark energy is, its effect is measurable, and its consequence is profound. Because if the expansion of the universe is accelerating, then its future is not a slow fading or a grand return. It is a race toward isolation. Over time, more and more galaxies will slip beyond our cosmic horizon, receding so fast that their light will never reach us again. The night sky will grow emptier, the cosmic web will unravel, the stars will die one by one, and the universe will become a place of cold silence, where only the remnants of local clusters remain visible, huddled together in an ocean of darkness that stretches forever. In this future, the universe is not ending, but it is drifting apart, piece by piece, unreachable and unseeing. And yet, even in this quiet desolation, the expansion continues, because dark energy does not diminish, it does not fade, its strength does not lessen as the universe grows. In fact, it becomes more dominant. As matter thins, as radiation fades, dark energy remains, and the more space there is, the more of it there is, because dark energy is not in things, it is in space itself. The more space stretches, the more energy fills it, and the faster it grows. It is a loop, a quiet, runaway loop, and it may never stop. So why is the universe getting bigger faster? Because there is something at work that we cannot see, something silent, something, a presence not of stars or gas or galaxies, but of pressure, negative pressure, that resists gravity, that fuels expansion, that pulls the universe open like a tide with no moon, like a breath that never exhales. And though we do not yet know what dark energy truly is, we know it is changing the destiny of every. Chapter 15. Could the universe be much bigger than we think? We stand on a small planet orbiting a medium star in a quiet corner of a single galaxy, and from this humble vantage point, we dare to measure the cosmos. We build telescopes, launch satellites, map the sky, and trace the light that has traveled for billions of years, just to reach us. And from all this we construct an image of the universe, its age, its shape, its content, its behavior over time. But for all the beauty in that image, for all the accuracy we've gained, we must remember a truth more humbling than any other. We are only seeing a fraction of the whole. A sliver, a limited bubble surrounded by an invisible vastness. And within that awareness comes the haunting possibility, perhaps even the certainty, that the universe is much, much bigger than we think. The part of the universe we can observe, what we call the observable universe, is limited by the speed of light and the age of time. Light moves fast, but not infinitely fast, and since the universe has a finite age, about 13.8 billion years, that means we can only see as far as light has had time to travel since the beginning. Because space has expanded during that time, the edge of our observable universe is now roughly 46.5 billion light-years away in every direction, forming a sphere about 93 billion light-years across. And yet, this is only the light we can see. It is not the edge of space. It is not the boundary of reality. It is simply the limit of what has had time to reach us. Beyond that cosmic horizon, there may be more galaxies, more stars, more clusters, more of the same, endlessly repeating across a canvas too large to paint. Or perhaps, beyond our reach, things begin to change. What lies beyond what we can observe? This is not just an open question, it is an urgent one, because the structure of space doesn't stop where our sight does. The universe may continue infinitely, stretching far beyond what our instruments can measure. And there is no reason, based on what we know, to assume that the cosmos ends at the edge of our view. In fact, every observation we make suggests the opposite. The large-scale distribution of galaxies, the smoothness of cosmic microwave background radiation, the uniformity of physical laws across billions of light-years, all of it implies that the universe continues, perhaps indefinitely, beyond our horizon. But just how much bigger could it be? Some models suggest that the entire universe could be hundreds, thousands, or even millions of times larger than the observable universe. Others go further still, proposing that space may be truly infinite, with no boundary, no edge, no limit at all. In such a cosmos, our observable sphere is just a pinprick in an endless ocean of stars, a single glowing bubble floating among countless others, each with their own contents, their own histories, their own unreachable truths. And if the universe is infinite, then all possibilities arise. Not just once, but countless times. Every possible arrangement of matter, every possible configuration of particles, every combination of energy and form, including, somewhere far beyond our view, another Earth, another solar system, another version of you. Reading this very sentence in a room that feels almost, but not quite, identical. This idea is not fantasy. It is a statistical consequence of infinity plus uniformity. Given infinite space with a finite set of building blocks, repetition becomes inevitable. Every arrangement of matter will occur again, and again, and again, separated by distances so vast that light from one region could never reach the other, even in the entire lifetime of the universe. But even if the universe is not infinite, even if it is merely much larger than what we can observe, the implications remain staggering. There may be cosmic structures so immense we cannot begin to detect them. Galaxy clusters arranged in filaments that span billions of light-years, voids larger than anything we've mapped, regions of space where the laws of physics play out the same, but the histories are entirely different. Perhaps there are zones where matter never formed stars. Perhaps there are areas where galaxies evolved faster, where time flows slightly differently, where the cosmic microwave background has a different texture. And beyond even that, there may be domains of the universe with different physics altogether. In some inflationary models, the universe is just one pocket, one bubble in a vast multiverse, where inflation continues eternally, spawning new regions with each quantum fluctuation. Each of these regions may have its own physical constants, its own version of gravity, its own shape of space. We may live in just one room of a mansion so vast it cannot be mapped from within. But we must be careful, because these ideas, while compelling, also come with deep uncertainty. We cannot see beyond the observable universe. We cannot measure what lies past the horizon. We can only infer, simulate, hypothesize. The universe may be infinite, or merely so large that we can never tell the difference. So how do we live with that? How do we build science inside a bubble we can never burst? The answer is found not in despair, but in wonder. Because even within the limits of observation, the universe tells us stories that hint at what lies beyond. The smoothness of temperature across the sky suggests a greater whole. The distribution of galaxies hints at endless structure. The silence beyond the stars invites us to dream not of endings, but of continuation. And perhaps that is the deeper truth, that the universe is not just vast, it is more vast than vastness, a scale beyond scale, a mystery that grows faster than our understanding. Could the universe be much bigger than we think? Yes, not because we lack imagination, but because the truth may simply be bigger than imagination itself. Chapter 16. Is the cosmic microwave background a map of size? There is a silence more ancient than any void, a silence that echoes not with emptiness, but with the faint and fading warmth of the beginning. It is not the silence of space, nor the silence between stars, but the silence of light stretched thin by time. A remnant from when the universe was young, dense, glowing. This light, this soft, invisible whisper, is known as the cosmic microwave background, or CMB. And though it hums far below the threshold of our senses, it is the oldest light in existence, the farthest thing we can ever see, and one of the most profound clues to the scale, structure, and story of the cosmos. To understand what the CMB truly is, we must journey back, not just billions of years, but to a time before stars, before galaxies, before atoms were even whole. Around 380,000 years after the Big Bang, the universe was a hot, opaque plasma of protons, electrons, and photons. Light could not travel freely because it was constantly scattered by charged particles. The cosmos was a fog of blinding brilliance, where no photon could move more than a short distance before bouncing off matter. It was not dark, but it was hidden, and then suddenly, everywhere at once, the fog cleared. As the universe expanded and cooled, It reached a threshold where protons and electrons combined to form neutral hydrogen atoms. This moment, called recombination, allowed light to finally travel without obstruction. The universe became transparent, and the photons released at that moment, billions of years ago, have been traveling ever since, unimpeded, redshifted by the stretching of space. Until today, they fill the entire sky with a cold uniform glow, just a few degrees above absolute zero. This is the cosmic microwave background. It is not just a relic, it is a snapshot, a fossil of light, a photograph of the universe as it looked in its infancy. And because that light comes from every direction, what we are seeing is not one place, but a shell, a spherical horizon around us, marking the limit of how far we can see into the past. Every point on that map corresponds to a point in space, now much farther away, from which light began its long journey to reach us. So when we look at the CMB, we are not just looking outward, we are looking backward in time, at the edges of the observable universe, at the very limits of light and causality. But more than that, the CMB is not smooth. It is speckled with tiny fluctuations, minute variations in temperature and density, no more than 1 part in 100,000. And those variations, those slight differences frozen into the ancient light, are the seeds from which all structure in the universe grew. They are the places where matter was slightly more or slightly less concentrated, where gravity began its long, slow work of pulling, clumping, shaping stars and galaxies out of a field of near-perfect uniformity. And in those patterns we find a map not just of what once was, but of how big space is, how it behaves, and how it came to be the way it is now. The scale of the fluctuations in the CMB, the size of the hot and cold spots, depends on the geometry of the universe. In a flat universe, those spots appear a certain size. In a positively curved universe, like a sphere, they appear slightly larger. In a negatively curved universe, like a saddle, they appear smaller. By measuring these angular sizes across the sky, we can infer the curvature of space itself, and in doing so we begin to answer the question, how big is the universe, really? And the answer the CMB gives us is clear, though not final. It tells us that space is flat, or so close to flat, that any curvature is beyond our current ability to detect. This means the universe is either infinite or so large compared to the observable part that it might as well be. It tells us that the structures we see today, the galaxies, the clusters, the filaments of cosmic web, were born from the tiniest differences captured in this ancient light. It tells us that the fabric of space is not random, but structured, governed by laws, stretched by inflation, shaped by a balance of forces too perfect to be accidental. But the CMB does more than tell us size. It tells us by measuring how the radiation has cooled down to just 2.725 Kelvin today, we can calculate how much space has stretched since it was released. It tells us how long light has been traveling. It gives us a cosmic clock, ticking not with seconds, but with wavelengths of faded heat, guiding us to the conclusion that the universe is approximately. It tells us about contents, about how much of the universe is made of ordinary matter, how much is dark matter, and how much is dark energy. Because each of these components affects how the early universe behaved, how it expanded, how sound waves moved through the plasma, how the light was released. The peaks and valleys in the CMB's power spectrum, the rhythmic fingerprints of acoustic waves rippling through the early cosmos, let us read not just size but composition. In this way, the cosmic microwave background is not a picture, it is a document, a ledger of everything that has ever happened since the first light broke free. And in reading it, we are reading the story of size, of scale, of stretch, of distances too large for imagination. So yes, the CMB is a map of size, not a ruler, not a number, but a glowing shell of evidence. It shows us the limits of the observable. It points beyond the horizon. It whispers of distances measured not in miles or light years, but in time, temperature, and geometry. It is the outline of what we can know and the shape of everything just beyond. And when you look into it, when you gaze at the data or at the simulated map rendered in shades of red and blue, you are seeing the walls of the greatest room ever built. Not by hands, not by tools, but by the slow cooling of a universe, learning how to become visible. Chapter 17. Can light reveal the edges of reality? There is something poetic, almost sacred, in the idea that all we know of the universe, every distant galaxy we map, every star whose story we record, every ancient explosion we catch in mid-fade, is brought to us by light, not by touch, not by proximity, not by stepping into space, but by waiting for light to arrive, one fragile photon at a time. Light is not just how we see, it is how we know. It is the carrier of truth across impossible distances, the thread that connects us to what was, and the only messenger we have when asking where the edges of reality might lie. Because light travels at a finite speed, and because space is so vast, the farther we look, the further back in time we go. To look into the night sky is to look into the past. A nearby star shows us its face as it was years ago. A distant galaxy shows us how it looked when dinosaurs still roamed the Earth. The cosmic microwave background shows us the infant universe itself, glowing dimly with the echo of birth. Light is time travel. Light is memory. Light is the only thing that can paint a map of what lies beyond our reach. But can it show us the edge? That depends on what we mean by edge. If we mean the edge of the observable universe, then yes, light defines it. The limit of our vision is the distance light has been able to travel since the Big Bang, stretched by the expansion of space. That boundary is not a wall in space, but a horizon in time. The most distant light we can observe comes from the surface of last scattering, the moment when the universe became transparent, and that light forms a sphere around us, 46.5 billion light-years in every direction, a glowing shell beyond which nothing has yet had time to reach us. This horizon is not fixed. It grows as time passes, because every year, light from farther regions arrives. Our vision expands. The observable universe enlarges, not because we move, but because more light catches up. And yet there is a cruel twist. While some light reaches us, some never will. Because the expansion of space is accelerating, there are regions of the universe so far away that light emitted today will never reach us. Not in trillions of years, not ever. Those galaxies have crossed a kind of event horizon, beyond which they are lost to our future forever. Their light is still racing toward us, but the space it travels through is stretching faster than the light can move. And so, in one sense, light defines the boundary of our knowable universe, not by marking a place in space, but by drawing a line in what can never be seen. It gives us a map, not to the edge of everything, but to the edge of access. But is there a true edge of reality? Does the universe stop somewhere, or bend, or repeat? Does light ever reach a place where it cannot go further? Not because it runs out of time, but because there is nowhere left to go. Here, science falls quiet. There is no evidence of a hard edge. No border where the universe ends, no sharp drop into non-existence. All our observations suggest that space is either infinite or so vast and smooth that no curvature or limit can yet be detected. Light has shown us much, but it has not found a wall. It has found a horizon. Yes, but not a boundary. It has found silence. Yes, but not a termination. And yet, in another sense, light reveals edges everywhere. Because light bends when it passes through gravity, it warps when space curves, it slows in a medium, it stretches in expanding space, it echoes when it scatters. Light behaves not as a passive line, but as a sensitive probe of the terrain it travels. Through gravitational lensing, we can detect the invisible mass of galaxies. Through redshift, we measure expansion. Through interference patterns and polarization, we read the early universe's structure. Light does not just show us where things are, it shows us how space is shaped. It reveals the edges between epochs, the transitions between eras in the history of the cosmos. It shows the difference between ionized and neutral gas. It outlines the dark spaces between galaxy clusters. It exposes the ripples left by inflation. It traces the shadows cast by black holes. Every photon, if we know how to read it, carries with it the story of where it came from, how far it has traveled, and what it passed through along the way. And perhaps most importantly, light reveals our own limits, not just the limit of our telescopes, but the limit of our understanding, the edge between the known and the unknown, the fine line between measurement and imagination. Because for all its brilliance, light cannot travel faster than light. It cannot leap across event horizons. It cannot pierce the absolute black of a singularity's heart. It cannot escape the geometry of expansion. And so, for every truth it reveals, it also whispers of all the truths it cannot reach. In this way, the universe hides its deepest secrets in plain sight, by letting light reach only so far, by building a reality that expands faster than illumination, by placing its mysteries just beyond the line where vision fails. So can light reveal the edges of reality. Yes, but only the edges we can reach, only the parts that have allowed light to cross the distance, only the sections of the infinite that have opened themselves to visibility. Beyond that, there may be more. There may be things we will never see, not because they do not exist, but because light will never return from them. And in that darkness, in that quiet, there is not just mystery, there is invitation. Chapter 18. How do galaxies show us the universe's scale? When we think of galaxies, we might first imagine spirals of starlight spinning slowly in the dark, delicate arms filled with suns, planets, dust and time. Or we might think of elliptical giants, vast, glowing orbs of stars clustered tightly, humming with the gravity of ages. But galaxies are more than ornaments in the night sky. They are more than the settings for stellar drama. They are mile markers, measuring sticks, breadcrumbs on the trail of creation. Because when arranged across the vast canvas of space, galaxies do not lie in chaos. They follow patterns. They form structure. They reveal scale, and through them we begin to understand just how big the universe really is, not just in numbers, but in form, in connection, in depth. There are, it is estimated, more than 2 trillion galaxies in the observable universe. Each one may contain tens of billions, even hundreds of billions of stars. Some galaxies are small, mere smudges in the fabric of space, while others, like giant ellipticals, stretch for hundreds of thousands of light-years across. But galaxies do not exist in isolation. They cluster, they form groups, they move in relation to one another, carried by gravity and expansion, forming a cosmic web that stretches across space like a neural map, a scaffold of structure on the largest possible scale. This cosmic web, the large-scale structure of the universe, is made up of filaments of galaxies, with immense voids in between, regions where matter is scarce and silence reigns. These filaments can span hundreds of millions of light-years, connecting clusters like threads spun across a dark room. And when we step back, far back, and map the positions of galaxies not just in space, but in time, we begin to see the skeleton of the universe itself. But how do galaxies reveal scale? They do so first through distance. When we observe a galaxy, we are not seeing it as it is now, but as it was when its light began traveling toward us. A galaxy 1 billion light-years away shows us a scene from 1 billion years ago. A galaxy 10 billion light-years away shows us a scene from when the universe was young, newly formed, raw and turbulent. Galaxies become time machines, each one a window into a different era. and by observing thousands, millions, billions of them, spread across all distances and directions, we begin to map the unfolding of the cosmos. We see how galaxies change, how they evolve, how their shapes become more defined, their colors more varied, their structures more complex. As the universe ages, we see the earliest ones barely formed, small and chaotic, cradling the first generations of stars. We see the mature ones, massive and calm, glowing with the long light of old sun. Galaxies show us how long space has been stretching, how much the light has been redshifted, how far the expansion has carried them, how old the paths are between us. And then they reveal scale through clustering. Galaxies do not fall randomly across space. They are shaped by the invisible pull of dark matter, collecting in halos, merging, forming structures that span unimaginable distances. By mapping how galaxies are distributed, how densely they gather, how far apart they drift, we learn about the density of the universe, the nature of gravity, and the underlying geometry of space. We see not just how far galaxies are from us, but how they relate to one another, how they trace the web of cosmic growth. The baryon acoustic oscillations, those subtle ripples imprinted in the early universe and frozen into the distribution of galaxies, act like a standard ruler. They provide a regular pattern, a spacing between galaxies that allows us to measure cosmic expansion across time. By comparing that ruler across different redshifts, different slices of time, we can see how the universe's expansion rate has changed. Faster, slower, then faster again. Galaxies are not just distant lights, they are records of space itself stretching. They also tell us about horizon size, the maximum distance over which matter and energy could interact in the early universe. This defines how structure could form, how large the first clumps of matter could grow. Galaxies in their scale and spread carry the imprint of that early constraint. By measuring the largest coherent structures, superclusters, walls, filaments, we infer how big the universe must be to contain them, how long matter has had to assemble, how wide the canvas must stretch to fit such strokes. And perhaps most profoundly, galaxies help us see the unobservable, because if the large-scale distribution of galaxies is uniform across the sky, if the structures we see in one direction match those we see in another, then we infer that the universe continues beyond the edge of our view, that what lies past the horizon is more of the same. Galaxies become a reflection not just of the visible, but of the hidden. We also see hints of scale in the way galaxies move, their peculiar velocities, their slight motions relative to the smooth expansion, reveal the gravitational tug of unseen mass, the pull of nearby clusters, the flow of cosmic tides, their redshifts and distances, compared in vast surveys. Let us chart the velocity field of the universe itself. Like buoys on a rising sea, galaxies bob and drift, marking the motion of space with graceful slowness. And then when we gather enough of them, we begin to see the true scale emerge, not just in distance, not just in time, but in structure. We see the Sloan Great Wall, a sheet of galaxies stretching 1.4 billion light-years across. We see the Hercules, Corona Borealis Great Wall, possibly even larger. We see voids so vast that light could travel for hundreds of millions of years and find nothing. And in those contrasts between presence and absence, between matter and silence, we feel the breath of the universe, the rhythm of scale beyond numbers. So how do galaxies show us the scale of the universe? They do not tell us with a single number. They do not give us a wall to touch, a ceiling to press against, a floor to stand on. Instead, they scatter themselves across space and time, each one a marker in a story too wide to hold, too long to tell all at once. They are beacons, frozen in their own pasts, woven into patterns only visible from great distances, from great patience, from the slow turning of cosmic time. And through them, the universe does not simply show us how big it is, it shows us how much it holds. Chapter 19. Do black holes hide hidden dimensions? There are places in the universe where the known laws of physics stop working, where light itself is silenced, where time slows to a crawl, and where space folds so tightly around itself that even the future becomes uncertain. These are not myths, these are not metaphors, these are black holes, and they are as real as the stars that orbit them, as tangible as the gravitational waves they release into space, as measurable as the X-rays they emit as they tear apart passing matter. But for all the progress we've made in understanding their behavior, black holes remain among the most mysterious entities in existence. And at the heart of that mystery lies a question so strange, so bold, that it feels like stepping off the edge of logic itself. Do black holes hide extra dimensions? To ask that question is to open the door to realms beyond our senses, because for centuries we've lived in a world defined by 3 dimensions of space and 1 of time. A neat 4-dimensional structure known as space-time. It is the framework in which everything unfolds. But what if that framework is incomplete? What if space has more than 3 dimensions, hidden ones, curled up, folded tight, unseen but not unfelt? What if black holes are not just gravitational sinks, but gateways to deeper geometries, windows into a reality more complex than we've ever imagined? The idea of extra dimensions is not new. In the early 20th century, mathematician Theodore Kaluza and physicist Oscar Klein proposed that electromagnetism could be unified with gravity if we allowed for a 5th dimension, a spatial one, beyond the 3 we experience. Though the idea faded for a time, it re-emerged with force in the latter half of the century through string theory, a framework in which particles are not points, but vibrating strings of energy, whose vibrations depend on the shape of the dimensions in which they live. In most versions of string theory, space must have not 3 but 10 or 11 dimensions, some large and extended like the ones we know, others compactified, curled into loops, smaller than atoms, woven into the very grain of space-time itself. And while these extra dimensions are too small to observe directly, they may still influence the physics we see. They may determine the strengths of forces, the masses of particles, the very fabric of the cosmos. So where do black holes come in? Black holes are regions where space-time is curved to its most extreme. They are not just objects. They are structures defined not by matter, but by geometry, by event horizons, by singularities, by warps, so deep that time and space trade places. If there are hidden dimensions, then black holes are the places where they may be most accessible. Not physically, not by travel, but by mathematics, by energy, by the subtle effects they leave on the observable world. Some theories suggest that small black holes, especially those formed in high-energy conditions like the early universe, or perhaps in particle accelerators, could behave differently if extra dimensions exist. In models where gravity can leak into other dimensions, such as in the Randall-Sundrum-Brandworld scenarios, the gravitational force might appear weak to us, not because it is inherently feeble, but because it is diluted across more dimensions than we can detect. In these models, gravity could become strong at smaller scales, possibly allowing black holes to form more easily, to evaporate more quickly, or to reveal unexpected behaviors that hint at hidden geometry. Even more provocatively, some hypotheses suggest that the singularity inside a black hole, the point where matter is crushed to infinite density, where general relativity breaks down, may not be a point at all. It may be a bridge, a passage, a region where the extra dimensions unfurl, where the rules of 4-dimensional space-time give way to something richer. In such a picture, the singularity could connect to another universe, or to another region of our own, or to a higher dimensional structure in which our universe is just a shadow. Of course, these ideas are speculative. There is no telescope that can see beyond the event horizon. There is no particle collider yet that can probe such extreme gravity. But there are hints. There are puzzles. Consider the information paradox. The apparent contradiction between quantum mechanics and general relativity when applied to black holes. If information cannot be destroyed but black holes seem to erase it, then something is missing in our understanding. Some theorists believe that the resolution lies in higher dimensions, where information may be stored or returned in ways we do not yet grasp. Or consider holography, the idea that everything within a volume of space can be described by information on its boundary, a concept born from black hole thermodynamics and now extended to the ADS-CFT correspondence in string theory, which suggests that a gravitational theory in a volume of space is equivalent to a quantum theory on its boundary. This radical idea connects gravity, quantum mechanics, and extra dimensions in a new and powerful way, and black holes are at the center of it all. So do black holes hide hidden dimensions? We cannot yet say for certain. But if such dimensions exist, if the universe is built from more directions than we can perceive, then black holes may be the cracks where that deeper reality shows through. They may be the cosmic laboratories where the unseen makes itself known, not by letting us travel to another realm, but by changing the way gravity bends, by altering the way particles decay, by leaving fingerprints on the radiation they emit, on the waves they send, on the very structure of space-time they disturb. Perhaps in the silence beyond the event horizon, in the place where space collapses and time stands still, there is more than darkness. Perhaps there is depth. Chapter 20. Could gravity be stretching space farther than we imagine? Gravity is the oldest force we've ever known, not because we discovered it early, but because it has always held us. Before we understood it, we felt it. Before we measured it, we lived by it. Gravity pulls the apple to the earth, the moon around the planets around the sun. It binds galaxies together. It sculpts the curves of space-time. But for all its familiarity, gravity remains the most mysterious of the fundamental forces, silent, elusive, and vastly weaker than all the others. And yet in that very weakness lies a possibility so vast it feels like a whisper from the bones of the cosmos. What if gravity stretches farther than we imagine? What if it is not just pulling objects closer, but pulling space itself outward, reaching across dimensions, dragging the fabric of reality in ways we have not yet begun to measure? In the classical view, gravity is a force of attraction. One mass pulls on another. Newton gave us the equations. Einstein gave us the curvature. But both, in different ways, told the same story. Gravity pulls inward. Gravity closes space. Gravity tightens. It binds. But as we began to look deeper across larger scales, greater distances, cosmic epochs, we began to see something unexpected. The universe is not just expanding. The expansion is accelerating. Galaxies are drifting apart faster and faster. The space between them is not held in place by gravity. It is unfolding, stretching. At first, this led us to a new force, dark energy, a mysterious pressure that acts opposite to gravity. But what if the answer lies not in some added energy, but in gravity itself behaving differently at scale? Some theories propose that gravity is not confined to our familiar four-dimensional space-time, but instead leaks into higher dimensions. In these models, called Brandworld scenarios, our universe is a three-dimensional membrane, a brain floating within a higher dimensional space, the bulk. Matter and light are confined to our brain, but gravity is. It spreads into the bulk, diluting its strength in our dimensions, but also extending its reach in ways we cannot directly observe. And in that extension, in that hidden stretch, gravity may be warping space far beyond our view. This means that on cosmological scales beyond galaxy clusters, beyond superclusters, gravity might not weaken as quickly as we expect. It might not be confined to local masses or short-range curvature. It might in fact participate in the very structure of expansion itself. Some versions of modified gravity theories like modified Newtonian dynamics, or FR gravity, attempt to explain galactic rotation curves and large-scale structure without dark matter or dark energy. They suggest that gravity behaves differently in the low acceleration regime, flattening out, becoming non-linear, altering the way space responds to mass. And if true, this would mean that gravity is not a simple law, but a complex geometry, adapting with scale, stretching not just space between galaxies, but space within galaxies, between stars, between the smallest and the large. And then there is the possibility that gravity is not a fundamental force at all, but an emergent phenomenon, a consequence of deeper principles such as entropy and information. In such theories like those proposed by Eric Verlinde, gravity arises from the statistical behavior of microscopic degrees of freedom, the way temperature arises from the motion of molecules. In this picture, space itself has thermodynamic properties, and gravity is a change in entropy as matter moves through space. Here, the stretching of space is not the result of a repulsive force, but of a rebalancing of underlying information, a tug-of-war not between masses but between bits. What makes all of this so haunting is how little we still understand. We know that space is expanding, we know the rate of expansion is increasing, we know that gravity binds galaxies and curves light. But when we step back far enough, when we ask how gravity behaves across billions of light years, when we let the math extend beyond the observable, we reach the edge of knowledge. We find only questions. Could gravity in its vast and silent way be the true architect of expansion? Could the same force that binds stars be the one that quietly pulls the edges of space apart? Could gravity stretch not as a pull but as a geometry, a ripple, a bending, that expands not toward mass, but toward emptiness? We know that gravitational waves ripple through space, that mass warps the path of time. We know that light bends, that orbits precess, that space-time itself is a canvas woven with tension. But perhaps we have only been looking at gravity through the narrow lens of the familiar, through the orbit of the moon, the fall of the apple, and perhaps beyond that lens, gravity is doing more than we imagined. Perhaps it is drawing space outward like a curtain. Perhaps it is smoothing the void like a tide. Perhaps it is not just the keeper of form, but the midwife of expansion, pulling the universe not in but forward. So could gravity be stretching space farther than we imagine? If it is, we may not see it directly. We may not measure it in a lab, but we might find it in the curves of galaxies, in the quiet flow of structure, in the slow acceleration of the void itself. We might find it not in strength, but in subtlety, not in what gravity pulls, but in how far it dares to reach. Chapter 21. Are there whole regions of the universe we'll never see? There is a comfort in believing that the universe is knowable, that even if we cannot reach its edges, we can at least one day understand them. That with better tools, stronger telescopes, more refined models, we might eventually piece together the entire puzzle. But what if some pieces are not just missing? What if they are unreachable? What if there are entire regions of space, entire realms of galaxies, matter, light and time, that exist beyond the reach of even our most ambitious vision? What if the universe is not only bigger than we imagine, but contains whole volumes we are fundamentally forbidden to ever see? To accept this is to confront the meaning of cosmic horizons. These are not edges in the classical sense. They are not walls, not boundaries that define where the universe ends. They are limits set by time, by light and by expansion. Barriers not of existence, but of information. We live in a universe that began That moment, the birth of space, time and energy marked the beginning of every path light could ever take. Since then, space has expanded, and because light travels at a finite speed, we can only see as far as light has had time to reach us. That limit defines the observable universe, a spherical region centered on Earth, roughly 93 billion light-years in diameter. Anything beyond that is simply too far away for its light to have arrived yet. But the story doesn't end there, because the expansion of space is not constant. It is accelerating. Galaxies are not just moving away, they are moving away faster with time. And this means that some regions of space, those far enough and moving fast enough, are crossing a point of no return. a threshold beyond which even light cannot make up the distance. These regions are not lost because they are gone, but because they are receding faster than light can catch up. This is not science fiction. It is the consequence of general relativity combined with observational cosmology. And it leads to a sobering truth. There are places in the universe whose light will never reach us. Not now, not ever. Not because they never existed, not because they are destroyed, but because the fabric of space between us and them is stretching too quickly for photons to bridge the gap. We call this the cosmic event horizon, and it is as real as the horizon of a black hole. It marks a limit to what can ever be known, not just now, but in principle. There are galaxies shining right now, whose light is already too far behind. It is racing toward us, but space itself is dragging them away faster. That light will never arrive. Those galaxies are already past the line of eternity, and in the far future this effect will grow. More and more of the universe will slip beyond reach. The night sky will grow darker, not because stars die, but because the stars that remain will recede from visibility. Galaxies will vanish one by one, not with a bang but with a fade. Civilizations, if they exist in those unreachable domains, will remain forever unknown, not because we lack the curiosity, but because the universe itself prevents the meeting. But it goes deeper still, because even now, at this very moment, we can only see a slice of what exists. If the universe is larger than the observable universe, and all evidence suggests it is, then there may be countless regions, each with their own galaxies, structures, stories, perhaps even physical conditions. These regions are not just far, they are causally disconnected. Nothing that happens there can affect us, and nothing we do can ever influence them. They are parts of reality that exist beyond cause and effect, as far as we are concerned. And if the universe is infinite, then there are infinitely many of them. This doesn't mean they are less real. It doesn't mean they are hypothetical. It means that our view is not the whole. It never was. It never will be. Our entire cosmic history, every star born, every planet formed, every chemical reaction and evolutionary path, has played out within a narrow band of an unfathomably wider continuum. There may be other regions with more matter, less matter, no galaxies, too many galaxies, other forms of structure, or simply more of the same, repeating endlessly, endlessly beyond our sight. In some inflationary models, this truth becomes more extreme. The universe may be eternally inflating, spawning new regions, new bubbles, each with their own expanding space, their own laws, their own causal horizons. We live in one such bubble. Beyond it are others, unreachable forever, not by distance, but by dimensional separation. And if this is so, then we are not just a small part of the universe. We are a causal island in an archipelago, without bridges. This is not cause for despair. It is cause for perspective, because even though there are regions we'll never see, perhaps an infinite number of them, we are still connected to a vast and rich portion of space. We are still recipients of ancient light. We are still part of a grand structure. Our observable universe, though limited, contains 2 trillion galaxies, each a cathedral of complexity, each a window into billions of years of cosmic history. And perhaps it is enough to know that we are seeing as far as nature allows, that we are leaning over the edge of the visible, listening for echoes from just beyond, that we are for a brief moment in cosmic time, awake and aware inside a universe that stretches on, not just beyond the horizon, but beyond the possible reach of memory itself. So are there whole regions of the universe we'll never see? Yes, but the miracle is not that there are parts we cannot touch. The miracle is that there is anything we can see at all, and that it is so vast, so rich and so beautifully unfinished. Chapter 25. If there's no edge, then where does the universe end? We are used to edges. Edges define things. They tell us where a table ends and the air begins, where the road stops and the field starts, where the body ends and the world begins. Our minds have evolved to find comfort in boundaries, but the universe, it seems, is not shaped by comfort. It is shaped by laws we are still struggling to understand, and among those laws is one that defies our every instinct. The universe, as far as we can tell, has no edge, no wall, no border, no outside. So then, where does it end? The question forces us into a space of paradox. Because if there is no edge, then how can the universe be finite? And if it is infinite, then what does that even mean? Not just mathematically, but physically, emotionally, experientially. The answer begins not in what we see, but in how space is shaped. In everyday life, we imagine space as a flat expanse, like an infinite grid, stretching out in all directions. But space, according to general relativity, can be curved. It can bend under the weight of matter and energy. It can loop back on itself. It can grow or shrink. It can expand, and crucially, it can be finite, yet unbounded, like the surface of a sphere, but in higher dimensions. Imagine standing on Earth. You walk in a straight line, always forward, never turning, and eventually you return to where you started. You never encountered an edge, you never fell off, yet your path was not infinite, it was closed. That is what we mean by unbounded, but finite. And the same could be true, in a higher dimensional sense, of the entire universe. In some cosmological models, the universe has positive curvature, like a four-dimensional sphere. In others, it is flat, extending forever. In still others, it may have negative curvature, like a saddle, infinite in all directions, but shaped differently. But in none of these cases does it possess a boundary, a place where the universe stops and something else begins. There is no outer shell, no void beyond. Space is all there is, not in the poetic sense, but in the literal, physical structure of existence. But then we must ask, if we cannot reach an edge, if there is no wall to cross, how can we even define the end of the universe? The answer, perhaps, is that the universe does not end in space. It ends in visibility, in causality, in contact. It ends not with a fence, but with a horizon, the cosmic light limit, beyond which no information can ever reach us. There are galaxies that once shared our cosmic past, but now are gone from our sight forever, moving away faster than their light can catch up. To us, they are gone, not because they ended, but because their presence has crossed into silence. So in a very real sense, each observer carries their own private universe, their own patch of space-time bounded not by structure, but by light's memory. Yet that boundary is not fixed. It grows as light from more distant regions finally reaches us, and it shrinks in other ways too, as acceleration carries some regions permanently beyond reach. We live at a crossroads, a moment when the visible universe is vast, but the reachable universe is already shrinking. The map is being written in light, even as parts of it are fading from view. And still the question echoes, if the universe has no edge, then what lies beyond what we see? The honest answer is, we don't know. Maybe more of the same, maybe variations, maybe nothing at all, because beyond our horizon, all bets are off. The laws we know apply only within our visible sphere. Beyond that we are blind. We can model, we can guess, but we cannot test, we cannot know. And yet, that boundary, the absence of an edge, does not make the universe feel smaller. It makes it feel deeper, because we are not standing at the center of a dome. We are not peering toward the edge of a disk. We are floating inside a structure that bends back on itself or continues forever. And either way we are inside it, not beside it, not outside it, not looking down on it like a map. We are within the unfolding of something that may not be meant to be finished. So where does the universe end? Maybe it doesn't. Maybe it's not a question of where, but of when. Maybe the universe ends not at a distance, but in a future, in a time when its energy spreads so thin that no structure remains, no complexity survives, no signal travels. Maybe it ends in stillness, not in boundary. Maybe it ends not in destruction, but in forgetting, as more and more of itself becomes invisible, intangible, unreachable, until the very idea of edge no longer applies. Or maybe it doesn't end at all. Maybe what we call an ending is only a transition to new forms, new geometries, new universes, budding off the side of this one. Maybe the lack of edge is not a void, but an invitation, an opening into the unimaginable. And perhaps that is the most honest conclusion we can reach, that the universe does not end with a line, but with a question, not a wall, but a wonder, not an edge, but a horizon of mystery that keeps moving, as long as we keep asking. Chapter 23. How does the size of the universe shape the fate of time? Time is something we move through without question. We measure it, divide it, obey it. We build our lives around the slow turning of hours and the invisible flow of moments, trusting that time is something external, something absolute. But in the language of the universe, time is not a steady drumbeat. It is not a background. It is not separate from space. It is a part of space, woven into its fabric, shaped by its structure, bent by its mass, altered by its motion. And so when we ask about the size of the universe, we are not asking only about distance, we are asking about how time itself is allowed to behave. The connection between space and time is not metaphorical. It is fundamental. According to Einstein's theory of general relativity, time and space are part of a single entity, space-time. They are curved by gravity, stretched by velocity, warped by energy. The bigger the universe, the more it curves. The faster it expands, the more time responds. There is no such thing as a clock that ticks independently of the cosmos. There is no moment untouched by the shape of space. So what happens to time in a universe of this size? First, consider the beginning. When the universe was small, tightly packed, hot and dense, time behaved differently. Near the Big Bang, the extreme concentration of energy and curvature meant that time barely existed as we understand it. The early universe was not a place of ticking seconds and quiet hours. It was a roiling quantum foam, a chaos of probabilities, a storm of overlapping forces with no fixed direction for time to flow. Only as space expanded and cooled did time settle into a smooth, forward-moving arrow. That arrow of time, the sense that past leads to future, is tied intimately to entropy, the spread of disorder, and entropy itself is tied to the volume of the universe. In a small, ordered cosmos, entropy is low, but as the universe grows, it creates more room for disorder, more places for energy to disperse, more futures than past. The bigger the universe becomes, the more it enables time to move forward. Not because something pushes it, but because the statistical weight of all possible futures is greater than the patterns already left behind. In this way, the size of the universe drives the direction of time. But the story does not stop there, because space is not just expanding. It is doing so at an accelerating rate, and this changes time in even more subtle ways. In a universe where expansion is constant, time continues along a well-defined trajectory. But in a universe where expansion speeds up as ours does, time begins to stretch, not evenly, not kindly. It becomes warped by the acceleration itself. The future becomes longer, the past becomes unreachable, and the separation between now and then grows wider. Eventually, if the expansion continues forever, distant galaxies will move beyond our horizon. Their light will never reach us. Their clocks, ticking far away, will drift out of sync with our own. Not because time flows differently in their region, but because there is no longer a path for their time to intersect ours. And as more and more of the universe slips beyond contact, time becomes fractured across distance. Each region of space, still moving through its own timeline, becomes causally disconnected. Each one evolves alone. The sheer scale of the universe, not just in size, but in continuing growth, means that time is not global. There is no master clock. There is no universal now. There is only local time, tied to the experience of observers, shaped by their motion, their gravity, their place in the cosmic expansion. You and I experience time because we are here, on this planet, within this galaxy, within this moment. But even now, there are parts of the universe so far removed, so warped by motion and gravity and expansion, that their concept of now does not overlap with ours at all. And then comes the question of fate, because the size of the universe does not just shape how time flows, it shapes how time ends. In a closed universe, one that is finite and curved inward, space would eventually stop expanding and begin to contract. Time would slow, reverse direction in a sense, or come to a halt in a final, crushing singularity. But in an open or infinite universe, especially one with accelerating expansion, time never loops. It never returns. It moves forward indefinitely, not toward an end, but toward ever-deepening silence. The larger the universe becomes, the more diluted energy becomes, the more isolated regions grow. Time does not stop, but it loses its richness. It loses the rhythms that once defined it, the birth and death of stars, the ticking of planetary orbits, the flow of heat. Eventually, in the farthest stretches of future time, there may be no processes left to mark time's passing, no motion, no change, no memory. And yet, time will go on. It will extend not as a story but as a line, a duration without event, a future without narrative. In this way, the fate of time is not to vanish, but to become pure form, duration without difference, continuity without content. Still, even in this strange fate, something remarkable remains. We are here, now, at a moment when the universe still pulses with time's full vitality. Galaxies still shine, stars still burn, minds still wonder. The size of the universe has not yet robbed us of meaning. It has instead made this moment possible. So how does the size of the universe shape the fate of time? It sculpts it, it stretches it, it sets its direction, defines its limits, and determines whether time can be shared or only lived. In a small cosmos, time is intimate. In a vast cosmos, time is fractured. And in an infinite one, time is an ocean whose shores we will never see, whose currents we can only ride, and whose depths are shaped by the very space we drift within. Chapter 24. Could we ever leave this universe? It begins as a quiet thought, a whisper rising beneath the weight of starlight and silence. The idea that this universe, vast as it may be, might not be all there is. That beyond the shimmering edge of the cosmic ocean, beyond the farthest galaxy, beyond even the farthest reach of imagination, there could be something else. Another space, another structure, another version of reality entirely. And once the idea takes hold, it becomes impossible to ignore the question, could we ever leave this universe? The word universe once meant everything, all of time, all of space, every law, every particle, every possibility. It was not a container, it was the whole. But now, in the age of modern cosmology, quantum theory and string landscapes, the word has fractured. It has become local, conditional, one bubble in a foam, one page in an infinite book. Our universe, the one we see, the one we live in, may be just a chapter, and where there is one chapter, there may be more. But leaving this universe is not like crossing a border. It is not like stepping from one room into another, because the universe is not embedded in anything else that we can point to. It does not sit inside a larger space. It is the space. So to speak of leaving it is to imagine something far stranger than travel. It is to imagine a rupture in the laws of nature, a passage not across space, but beyond the fabric of space itself. Still, theoretical physics offers glimpses, not maps, not paths, but hints, whispers, clues that something more might exist just beyond reach. In some versions of inflationary cosmology, the universe is not a singular event, but part of an eternal process, a cosmic sea, where bubbles of space-time constantly form and expand. Each bubble becomes a universe with its own laws, its own constants, its own unfolding of time. We live in one such bubble, and if that is true, then there are others, vastly many, forever out of reach perhaps, but still real. And between these bubbles may lie boundaries, domain walls of intense energy, places where space is thin, distorted, unstable. If a bubble collides with another, a new region might be born. But could we ever pass through? Probably not. Not in any way we understand. Because the forces that stabilize our bubble are immense. The constants of nature, the balance of particles and fields, the shape of space-time, all of it is finely tuned. Crossing into another bubble, if even possible, would mean entering a realm where everything changes, where atoms might not hold, where gravity might crush or vanish, where light might behave in ways we cannot survive. The act of leaving this universe could be the end of all form, the dissolution of structure into something unrecognizable. And yet, theory offers other doorways. In the realm of string theory, space is not smooth, but curled, woven with extra dimensions, tightly compactified and hidden. If those extra dimensions are real, if they extend beyond the familiar four, then there may be ways to fold space in ways we do not yet understand. Some propose that wormholes, hypothetical tunnels through space-time, could connect distant regions or even different universes entirely. In this view, the universe is not a closed room, but a woven manifold with secret passageways through higher dimensional corridors. But such passageways, if they exist, are fragile. They would require exotic matter, negative energy, strange geometries just to remain open. And even if one were found or made, we do not know what lies on the other side. Another region of this universe, another brain in a higher dimensional bulk, a quantum echo of our own cosmos, and then there are the ideas born from quantum mechanics itself. The many worlds interpretation suggests that every quantum event creates a branching, a splitting of realities, each consistent, each real, each containing a different version of what might have happened. In this view, the universe is constantly proliferating, not outward in space, but inward through possibility. Could consciousness, could information traverse those branches? Could some version of us find a way not through space, but through decision, through quantum state, to step sideways into another world? Or are these worlds forever parallel, never touching, as unreachable as a dream you cannot return to? Even more radical ideas suggest that the entire universe is a simulation, a vast and intricate computation run by some deeper layer of existence. If this were true, if our universe is code, then leaving it might mean breaking the simulation, hacking the source, stepping beyond the rules that bind the virtual to find the real. But such ideas, while fascinating, remain speculation stacked upon speculation. They tell us more about our imagination than our physics. Still, even in the face of impossibility, the question remains, could we ever leave? Not with rockets, not with machines, not by moving through space, but maybe, just maybe, by understanding more, by uncovering the true structure of the cosmos, the hidden symmetries, the buried dimensions. Maybe what we call our universe is a shadow, and true movement lies not in velocity, but in transformation. Maybe the boundary between universes is not physical at all, but mathematical. A shift in constants, a change in symmetry, a new phase of the quantum field. Maybe the key is not to leave the universe, but to unfold it, to reach into the layers we have not yet touched, to reveal the more that has always been there, waiting. So could we ever leave this universe? Perhaps not as travelers, but perhaps as witnesses, perhaps as discoverers, perhaps by expanding not across distance but inward, toward understanding. Because in the end, the question may not be whether we can leave the universe. It may be whether we can ever fully know the one we are already inside, this strange, beautiful, impossible structure, where space is time, where light is memory, where thought has arisen in atoms, and where every question opens another door. Chapter 22. What happens if the universe keeps growing forever? The thought of forever is unsettling, not because it is dark or cold or vast, but because it never ends. We are beings built for rhythms, the rising and setting of the sun, the arc of seasons, the ticking of clocks, the cycles of breath. We are comforted by endings, even gentle ones, because they give meaning to beginnings. But when we stare into the universe and ask what happens next, we are forced to confront the possibility that there is no cycle, no return, no curtain to fall. Only the infinite continuation of everything expanding, cooling, drifting apart into a silence that becomes not a moment but a destination. For most of human history, we believe the universe was eternal and static, unchanging, a backdrop for everything else. But with the advent of modern cosmology, we discovered that space itself is dynamic. The galaxies are not sitting still. They are rushing away from one another, the fabric of space stretching like a rubber sheet under tension. The more we look, the more we see. Not only is the universe expanding, but that expansion is accelerating, driven by something we do not fully understand, an invisible pressure we call dark energy. And if this expansion continues, if the acceleration does not slow, reverse, or collapse, then the universe will grow, not just for billions of years, not just for trillions, but forever. What does that mean? What becomes of time and structure in a cosmos that refuses to rest? It begins slowly, subtly. Already today, galaxies outside our local group are moving away from us faster than we can ever travel. In the future, they will recede so quickly that their light will redshift beyond detectability. One by one, they will fade, not by dying, but by becoming invisible, unreachable, severed by the acceleration of space. We will not see them vanish in a flash. We will simply wake up one cosmic morning to a sky with fewer stars, fewer galaxies, fewer messengers of the distant past. Eventually, only the closest companions, Andromeda, the Milky Way, and a few small galaxies will remain gravitationally bound. They will merge into a single massive elliptical galaxy orbiting slowly in an ocean of darkening silence. No more external galaxies will be seen, no new light will arrive from beyond, and still, space will continue to grow. Stars too will fade. Over trillions of years, new star formation will decline as gas is used up. The youngest stars will burn out. The old ones will dim into white dwarfs. Neutron stars, black holes, planets will drift in darkness. Collisions will become rare. Energy will spread thin. The age of starlight will end, not with an explosion but with a slow ebb into shadow. And still, the universe will expand. Entropy, the great dissolver, will rise. Structures will flatten. Heat will even out. Gravity will hold the last remnants of matter in loose clusters, until even they are pulled apart by expansion or collapse into black holes. Over unimaginable time spans, Even the black holes will evaporate through Hawking radiation, emitting their last quantum sigh into the void. The timeline of such a universe is almost beyond comprehension. Stars may last for trillions of years. Black holes may endure for 10 garens years, an age longer than all of cosmic history so far, multiplied 1 billion-fold, and still just the midpoint. And when even the black holes are gone, when no matter remains to cluster, no energy remains to move, no light remains to illuminate, there will still be space, there will still be time. The universe, now empty, cold, quiet, will still be growing. This is the scenario called heat death, or the big freeze. It is not a death of destruction, but a death of potential, a time when the universe becomes too spread out for complexity, too sparse for motion, too diluted for life, or information or change. A time when everything that could happen has already happened, and all that remains is the slow aging of space itself. But some theorists speculate that expansion could do more than freeze. If dark energy evolves, if it grows stronger over time, it could lead to a more violent end, known as the Big Rip. In that future, the acceleration does not stay constant. It increases faster and faster. It pulls galaxies apart, then galaxy clusters, then star systems, then planets, then atoms themselves. Even the fabric of space-time tears, as if reality could no longer hold its own shape. The Big Rip is a universe undone by its own expansion, shredded not by heat or pressure, but by the relentless acceleration of nothingness. But even without a rip, even with a quiet freeze, the question remains, what happens to meaning in a universe that never ends? What becomes of purpose, of memory, of presence, in a cosmos that will one day forget its own beginning? Perhaps the universe keeps growing not because it must, but because it can, because in the equations that describe space and time, there is no built-in end, only condition. Perhaps our longing for finality is a feature of life, not physics, and perhaps the universe will not truly die, perhaps it will transform. Some ideas suggest that quantum fluctuations in empty space may, over enough time, trigger the birth of new universes, pockets of inflation that bud off like seeds. In that view, the endless expansion is not a winding down, but a foundation for new creation. Even in a universe that grows forever, mystery remains. The expansion does not rob the present of its wonder. It makes it more precious. Because in this moment, right now, we are able to see galaxies. We are able to witness starlight. We are able to ask. We are able to exist in the slim window between origin and infinity, a window where matter forms, where complexity rises, where thought emerges. We are alive in the part of the universe that still shines. So what happens if the universe keeps growing forever? It becomes quiet, it becomes dark, it becomes vast beyond reckoning. But perhaps it also becomes fertile, not in ways we can witness, but in ways we can imagine. And even in the silence, there is something unspeakably beautiful about a reality that refuses to collapse, that chooses instead to open, to stretch, to continue, not with a bang, not with a whimper, but with endless becoming.